Hello, hello. Let's see if my audio is working. Looks pretty good. All right, welcome to Average Expectations. Last week I had a test stream that went about as well as a test stream would go. So today we're going to do some real stuff. So let's go over the basics first. So this is a stream about various AI, programming, math, gaming, music types of projects. There might be some other things snuck in depending on how interests go. I'm streaming on YouTube for now, and it's Fridays every night starting at 8 p.m. This is Eastern time here. Couple rules, very simple. Basically, everyone's welcome. Please don't harass anyone, don't solicit, don't spam, and finally, no personal information. So I'm not sharing, and neither should you. Now, I am a TA for a course. If you have any really specific questions, like something that's personal or related to that course, please contact me through the official methods. But you can message. Of course, feel free to use chat to kind of ping me. I suspect that's going to be a lot more relevant next week when the first problem set is due, and there will be some people looking for last-minute help, even though I did ask everyone to start early because, with these kinds of proof-based assignments, it can take a long time to get things done, and for the context, I'm TAing a kind of how to write proofs math course. So that's not the kind of thing you can do last minute. Okay, so that's that. Projects. So last week I just tried to get my old Leonard Cohen voice deepfake running, and I did barely make it work. It took something like 5 hours, which is ridiculous, I think I basically spent an hour just messing with Docker containers and installing things. That was ridiculous. But this week, I'm going to be starting on some music projects. And the reason why is, I've actually have some composing. So before I started doing math stuff, I used to be a music teacher and a composer. And I still do write music, not very often, but I do. And so as part of this, I do need to create a program at some point to do some, it's kind of like a utility for synthesizing or creating piano music that kind of synthesizes a different sound. So that'll be a little later, but I thought this would be a nice kind of warm-up opportunity to try something that's a little adjacent to that. And basically, that's going to be today's project. 12-tone, all the things. I'll get into that very soon. But actually, let's get into it right now. So, and oh, look who's here to say hi. This is my cat. One of them. Hello. You want to say hi to the camera? No. Okay. Bye. She doesn't like to be held. Anyway, you might hear her in the background. Hopefully, she won't be too loud and annoying. Sometimes she's looking for food around this hour. Okay, so let's jump right into Project 1, which is tentatively called the Schönberger. Okay, so little bit of backstory. The man you see in the bottom right corner, his name is Arnold Schönberg, and he was one of the most influential classical music composers of the 20th century. And when I say influential in the 20th century, I really should say that he was mostly influential to other classical music composers. And so really, he's not influential to anyone like in the broader world, you could say. Only nerds like me care about him. So anyway, he was very influential because he came up with this idea along with his two students. His two students were Alban Berg and Anton Webern, and they were all in Vienna, and they came up with this new kind of classical music called serialism, also known as 12-tone music. And so, I was going to jump into this agenda, but I think we need an extra slide here, and we need the backstory. Oops. Yeah, in case you're wondering why I'm having trouble typing, this is not my usual computer. Shout out to my wife for lending me her rig, which is great for streaming. It's got all the stuff set up, but unfortunately, I'm not always used to the system. Sometimes if you see me opening up the Windows menu all the time, it's because I usually use Ubuntu, and it's got a handy feature where it shows you all the windows at once when you hit the Windows key. So now I just spam it uselessly like this. Anyway, okay, back to the backstory. So Arnold Schönberg, and co. And that would be Anton Webern and Albenberg. I think that's how you say it. Were the called the Second Viennese School. And so you might be wondering, if they're the Second Viennese school, who's the First Viennese School? And the answer is, we don't really know. You know, it's kind of like how Hitler decided to call, you know, the Nazi Empire the Third Reich. And it's like, what's the First and Second Reich? You know, it's like, they just made stuff up, right? That's what people do sometimes. So the Second Viennese School, though, the First Viennese School is arguably Beethoven, Haydn, and Mozart, but they didn't call themselves that at the time. Right. So the important thing is, though, people did call these three, Schönberg, Webern, and Berg, the Second Viennese School, and it was because they invented, serialism. 12-tone music. Okay, and what is serialism or 12-tone music? It is basically music where you have to use every note in the chromatic scale once, and then you can use them again. And basically, the idea is you can't repeat a note until you've used it before. And when I say the chromatic scale, it means every single key on a keyboard, right? Except like until it repeats. So on a piano keyboard, let me pull up a picture. So where's a nice keyboard picture? Maybe this will be nicer. Nope. Okay, this is probably the best I'm going to get right now. So, wow, why does that have two manuals? Okay, one manual. That's a lot more typical piano. So you can see that on a piano, you have the black keys, you have the white keys, and eventually they repeat. After 12 keys, they repeat. So that's one octave. And within an octave, you have 12 different keys, and each one has a different name. Usually there's 7 letters, and then there's also some sharps and flats you throw in order to make the black keys have names. And those are just modifications to the letters. The important thing, though, is there are 12 keys. And in 12-tone music, you can only use a key if you've used like the previous, like basically, if I hit this A here, I cannot go back and hit the A until I've hit everything else within that octave. Right, so that's 12-tone music. And in case you're wondering how that sounds, I would say most people would say it sounds terrible. It's actually not exactly a pleasant sounding kind of music, because the entire point of serialism was to basically break away from the kind of romantic tradition of classical music that was happening before that, which was all about this kind of like very complex harmonies, but tonally based harmonies. And when I say tonally based, I mean like basically that you have a certain note, like for example A, which is like the tonal center of a piece of music, and we would call that the tonic. Right, so then you have things like A major and A minor. So those would both be kinds of collections of tones which kind of revolve around the A. And they really wanted to get away from that. So they were basically the down with tonality gang. And that's why they invented this kind of music. No tonics, no dominants. So what that really means for non-musicians is there are no notes which dominate the harmonies. It's all equal. It's like communism for notes, basically, right? Every note is equal. Everyone gets to be played a similar amount at a similar rate, because, you know, every 12 notes you have to play one of each note every time you go through 12 notes, and it's over and over and over. So the result is something that sounds kind of what we call atonal. And I mean, I'm not going to go into the details of this. Look, I have an undergrad in music, but I have not studied music history or music theory, you know, at a graduate level. I can't really tell you all the details and nuances of, you know, this history. I'm just kind of giving you the Cole's Notes version here. So, so far we've covered, you know, okay, we have these people, they invented this kind of weird music, and the reason why they did it was to break away with the past, because they did this around the 1920s, you know. This is kind of the time when people were experimenting with modernist art. They were moving away from the past, and pretty soon we moved away from that very, like, literally with the world wars, and kind of, you know, threw away the old world, you could say, the dominance of European culture and music. Yeah, I learned all this in, you know, music school, yada yada yada. It's part of your required, you know, courses, and that was like 10 years ago, right? And since then, sorry, I keep hitting this mic. Since then, what have I done? Sorry, I'm just gonna add one more caveat here. Uses all 12 notes equally. Okay, so that's the backstory. Now, you might be wondering, why do I care? You know, if this music sounds bad, and I'd say, like, even I don't really like it, and I have used it before in some of my compositions, why do we care about this? Well, for one thing, this is like, why not? You know, this is one of those things where it's like, just because you can, maybe, what do they say? Yeah, maybe you shouldn't, even if you should, whatever. You know that Jurassic Park quote. But anyway, so one thing is I wanted to try it just for fun. I've built something much more primitive to do this before as part of some composition project, and this was before I got into machine learning and all that stuff, programming, seriously, mathematics. So this was many years ago, and I'd like to revisit that, make it kind of more streamlined, better, faster, you know, 12-tone, all the things. But the other big reason why I wanted to do this is, well, recently there was, like in the last like couple days, there was a paper that kind of blew up Twitter and is making the rounds. I think, you know, I'm gonna look it up right now. Git rebasing. Yeah, this one. So I'm really sad about this because as great as this paper is, like in terms of like it's interesting and it's obviously gotten a lot of traction around, it was also the project that I just started like 2 months ago. And I'm really sad about that because we were kind of doing the exact same things. And turns out there's other people that were doing this. And I thought like nobody would be doing this, you know, when I started the project. It just seemed kind of obscure and like, who cares, you know? But the basic gist of this project is that you have a bunch of, well, I mean, let's talk a bit about it. So the basic idea behind this is that neural networks can be permuted, which means you can reorder some things inside them. And neural networks are just like, you know, the kinds of programs that I study, you know, things that can be used to predict other things, computer programs, right? But the point is that inside each neural network, you have a bunch of little like computer virtual neurons, and you can mix them up. You can mix up the order of those without changing the output, right? It's like if I took, you know, 10 circuits and I just like took the first circuit and moved it down to the third circuit and moved the third circuit back to the first circuit, and I keep all the wires attached, right? I'm just changing the order. And so obviously that doesn't change the overall circuit. You're just changing the form of it. But there is a situation in which that change matters. And that is when you're trying to kind of like average between two networks, right? So this doesn't affect how they work. But when you try to when you average between two networks, it doesn't work anymore. That doesn't work anymore because it's like, imagine if you had like one one circuit which does, let's say it does addition, and the second circuit does multiplication, or let's say subtraction. That's simpler, right? So you have addition circuit, then subtraction circuit. Now in the other network, you switch them around. You have subtraction first, then addition. Now, if you try to kind of average between those, because these neural networks are just a bunch of weights, if you try to interpolate, that's the technical term, between addition and addition, that works. You still get addition. Same with subtraction to subtraction. But now we've kind of swapped it around, right? We had addition, subtraction, and now we have subtraction, addition. So it was interpolating, averaging from addition to subtraction gives you some kind of garbage nonsense in the middle. And similarly with the other one, right? So basically what you want to do then is, if we wanted to do this kind of averaging, we might want to kind of permute the networks to some standard form. So this seems like a really long segue, right? I was talking about music, now I'm talking about neural networks. What happened? Well, basically, the permutation is the thing that's the same between these two projects. When you're permuting two networks, basically what you're really doing is, like here, I'll show you an example of a permutation, right? Let's say I have a neuron called A and a neuron called B, C, D, E. Let's say 5 neurons, right? Here's a permutation of those. I just changed the order around, right? And you can, of course, do this a lot of different ways. In fact, there are, let's see, 5 to the factorial ways to do this. And the reason why there's 5 to factorial is because you have 5 choices for the first thing, because we have 5 symbols here, right? So 5 choices for the first position, and then that leaves you 4 symbols left for the next position. So then you have 5 times 4, and then 3 symbols for this, and then 2 and 1. So basically the idea is, you have a list of 5 symbols, 5 things you're ordering, and then you insert one at a time. And every time you do that, you have one less choice as to what you have left to insert next. So that gives you all the possible permutations. And you might be wondering, how the heck do you actually find the optimal permutation? You want some standard form. Well, turns out it's really easy if you have something called a loss function. So I promise this will be relevant to music later, because we're probably going to have to mess around with this loss function. So the idea is that we need a way to decide how good a permutation is. You can think of this as like, if I have A in network 1 and I have like A prime in network 2, we need to know, like, how close are they together? How if I match up A with A prime, is that a good match or is it a bad match, right? It's like Tinder for neurons. And so the way you do that is with a loss function. So in the case of these kinds of papers, like this guy, what they do, and it's basically exactly what I was doing. That's part of why I'm sad about this project, right? Because we were doing the same thing. But what they're doing is basically the neuron 1 here. Let's say neuron A in network 1 has some weights. Let's make a little matrix. Let's just make a vector of weights because that's easier. So we'll have, like, let's say 0.4, and I don't know, 1.2, right? The numbers don't matter, right? It's just like for demonstration. So here's your weights from network 1, neuron 1, and then in network 2 you have like 0.6, let's say, and 0.8. And so you can see these weights don't look terribly similar. They're okay, right? Like, this one's smaller, this one's bigger, same with here, but they're not really the same magnitude in size. Okay, so that's kind of an okay match. But what if network A also has network 2 here also has a different neuron? Well, let's put these in the same line so we can see which is which. So here we have neuron A with these values, neuron A prime with these values, right? And then now we're going to have a neuron, let's say B prime, which has like 0.4 and 1.19 or something, right? So you can see that this neuron looks way, way, way more similar to this one. And we really should match up these two together, right? They're like, you know, love at first sight, match made in heaven. So to actually measure how close these matches are, we need that loss function, right? So just to fill this out, let's have another B prime neuron, which is like, let's say 0.6, 0.7 or something like that, right? So you can see that if I match up A to A prime, you're gonna have a bigger distance maybe than B to B, than A to B prime, right? And then, so basically we want this match. We want this match like this. That's a good one, right? And what's bad is if we match it up this way. And to measure that, what we can do is create a loss function. And that's just some calculation we do on these weights. And the easiest one is what we call like an L2 norm, right? So that's the distance calculation in Euclidean space. So in this case, loss of A and A prime would equal, you take the difference between them, so 0.6 minus 0.4 for the first weight. And you square the answer. You know, can I? Yeah, I can do this. Okay, and then you do the same thing for the second one. Yeah, and I apologize if you're, you know, you're familiar with deep learning and you know all this stuff. And I'm trying to be thorough this time because last stream I kind of just glossed over a lot of details. So, you know, this is a way to calculate loss. There's lots of different ways you could do this, right? This is just one way. So it's pretty clear this number would be kind of big. You know, should I do this? Okay, I'll do it. Mental math. 0.2. This is 0.4, so this would be 0.04 plus whatever this is. 0.4 squared is 0.16. Right? Wait a sec. Yeah, that's fine. So that would be 0.2. Okay, and then the loss of, let's say, B prime. Sorry, B and B prime. That should not be B prime. That would be what? You know, let's try it this way. A to B prime. Okay, so that way we get these two options. That's better comparison, right? And let's just call this 1.2. Makes it easier, right? Would be 0.4 minus 0.4. I'm just gonna copy this. And I promise we'll get to the music soon. So 0.4 to 0.4. 1.2 minus 1.2. Oh, look at that. Everything's 0. So the loss is 0. And that's basically what you do. Now, of course, you have a certain number of neurons in network 1 and a certain number in network 2. Let's call that n. So if you have n things, and you need a loss function, if you need a loss function between n and n things, you have n times n pairs, basically. Now, of course, in practice, it's a little less than that because, like, if you have A to B, it's the same as B and A, right? Loss functions are usually symmetric, which means it doesn't matter which order you put these things in. But the point is that the easiest way to represent this is by an n by n matrix or table of values. So what you end up with is if you have n things to match up, you compute a n times n matrix loss. Right? So what does that look like? Let's draw it out. Make a little table. So it kind of looks like this. Little table, and you have like first loss, second loss. Oops. Wow, it's kind of terrible, isn't it? Why is it so dark? Yeah, that's much better. Okay, so let's say you've got A, B, and C as your items in each matrix, and I'm going to call one of them A prime, B prime, C prime, and the other one just A, B, C. So it's going to look something like this. And then you're going to repeat, rinse and repeat for the other ones, except now you have B, 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 and C, C, C. So you can see this gives you every possible pairing between these things. In fact, it gives you a few extra because this C and A prime is, wait, is it? No, it's not. It's actually different. All right, because these are two different matrices. Sorry, I forgot that you have n things in one network, and you have n things from a different network. So these things aren't necessarily the same. So this matrix is not necessarily symmetric. Now, if you're doing it with the same things, right? If you're matching n things to themselves, this would be symmetric. But anyway, that's kind of beside the point. What you end up with is this, and then what you want to do is we need to find the smallest combination of losses, right? So the idea is that if I can match up A to A prime, and that was the smallest loss, and then if I can match B to B prime and C to C prime, then that would be the permutation, the ordering that gives me the best matching back to here, right? When you're doing this, right? The best matching was like this. So that's what we're looking for. And that answer, when you have that, has the lowest loss, right? So this, if I switch it back, this would have higher loss than this, right? But there's one problem, which is what we can't have is this, where you have A getting matched up to both things, because you need to match one thing to one thing at a time, right? In math terms, we need a bijective function, a function that is invertible. It goes both ways. You know, it's like partnering up at a dance. Everyone gets one partner only. You can't have one person having three partners, at least with kind of those kinds of dances that you get at a social dance, typically. Trying to be inclusive. Let's not make too many assumptions about those, right? But the point is, there's a kind of pairing that goes on here, which is what we need here. So what we can't do is we can't just pick everything in the first row here, because then you would match up A with multiple things. You couldn't do everything in one column either. Actually, the very specific thing we need for this permutation to hold is we need to match up exactly one thing in every column and exactly one thing in every row. It's like Sudoku, basically, right? So let's do that. I'm just going to highlight, some random cells to give you an idea of what a permutation might look like. So we're going to pick the lowest losses in a pattern where you have one thing selected in every row and every column, just like this. Right? So this is an example of a permutation. So we'll call this finding an optimal permutation. Now, the way you do this is through linear programming, and the good news is people have already coded up ways to do this. So I don't need to do anything for that. I can just import SciPy and I'm done. I can just run someone else's code to do this. And it's really, really fast. So that's the advantage of doing it this way. So that's basically what this paper did as well. If you skip ahead to, let's see, permutation selection methods, they talk about this, matching weights. This is where they do it. And they say, so it says there is a way to apply LAP, linear assignment problem, directly to this problem. There's some more details, but I'm not going to go into that. So anyway, so far so good. We have a way to do this, and then of course, when I was doing this with neural networks, I found out, oh, hey, someone else has already done this. They just published a paper. They didn't publish. They dropped it on arXiv, but it's kind of the same thing in machine learning these days. So what does that mean? Well, we're kind of hooped at this point for that project. I'm not sure what's going to happen next. But the good news is we can actually do the same thing to notes. What about 12-tone music? Okay, so the reason why there's a connection here is because permuting things is exactly what you need in order to make 12-tone music happen. So, for example, let's have some notes. We'll have C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B, C. Is that 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, right, and we don't want another C. That would be a repeat. You'll notice there's some gaps, right? Those correspond to where there's gaps between the black keys. You can see right here. Right, there's a gap. Oh, sorry. There's 2 gaps, and then they repeat. Those are exactly between E and F, and then B and C up here. Right. So anyway, you have 12 notes, and basically the way 12-tone music works is I can use these notes exactly once in every 12 notes, right? And then for the next 12 notes, I have to use exactly these again. So how can I make music, arbitrary melodies and tones? Well, I could swap these around, right? So I could play the F earlier here, right? I could play the D sharp at the end. I could play the B, let's say, in the middle. So you can see this is still 12-tone music. But what I can't do is, for example, I can't do this. I can't play 2 C's in a row. I can't play the E and then go back to C, right? I can't go back to any note here until I've hit all 12. So really, a way to think about generating 12-tone music is that I have just all 12 notes repeated over and over again, and then within those 12 notes, I get to permute them however I like. I can swap the order as much as I want, but what I can't do is have a different number of any given note. I can't repeat some or take some away from this sequence. Right? So that looks like a permutation. So really what we're doing here is we're permuting 12 tones. Every 12 notes in the piece. Okay, so that's the connection. And because my project on neural networks got scooped, I guess I'm gonna do this instead as consolation prize, right? We will automatically generate 12-tone music, and the idea is that here's kind of the basic setup. We are going to have, let's see, we're going to take some input music. We need to split it up into 12 note chunks. Right? And then basically we need to map that each 12 note chunk to basically a 12 tone row. And I'm going to call this a tone row because that's what Schönberg called it. The idea was that every time you have exactly 12 of these distinct pitches, we call that a row of the system. There's a lot of weird terminology with serialist music, where it actually ends up sounding an awful lot like math. It's like they were trying really hard to be math, and I remember learning this in music theory classes, and then I later, many years later, I went into basic proof writing courses, and we learned about in the music theory class they were talking about set theory, this way of organizing your intervals and tones in music. And then I go to math and they talk about set theory. I'm like, yeah, those musicians didn't really know what set theory was, from a math standpoint. That didn't make much sense, back then. It's kind of funny. They used all the language of mathematics to kind of lend legitimacy to their theories at the time in music. But it's really not the same thing. So the point is that they had all these 12-tone rows, and they would make matrices of them where they're basically just shuffling them around, reordering things. And then they would in fact, I have a picture right at the front. So this guy right here, if I zoom in, if I zoom in, yeah, this is a 12-tone matrix right here. Right, I've crossed it out because that's not what we're doing today. We're not doing this by hand, which is kind of what people like Schönberg did, right? And what you'll notice is that if you kind of look at it from certain directions, like if you look at the bottom side, what you can have is like an inverted version and a retrograde inverted version, which just means playing it upside down or backwards. Right? So inversion means instead of going up with a given note, you go down with instead. Yeah. So that's kind of the old-fashioned way of doing it with a handwritten 12-tone row and 12-tone matrix, and we are going to automate all that away because that's what we do. That is the purpose of computers. So let's see, where are we? We get some music, we split up into 12-note chunks, we map each one to a 12-tone row using permutations. So I guess this would be like optimizing, like we're running optimization, but we're finding a permutation. That's how I describe it, right? So optimization is like minimize this loss function. And then in this case, we are restricting our options for minimizing this loss function to permutations only. Okay, we can't just use any arbitrary notes. Okay, so this is kind of the meat and potatoes of what we're doing here, right here. That's the mathy bit and the programming bit. And then I guess we play it back. And probably let's split up the kind of central thing here, which is we need to split. Well, we already talked about this, right? Split into 12-note chunks. So we need to figure out a loss function. That's important here. And we also need to run the actual permutation finder. So we'll just call that optimize. Now, I think the loss function will be the hard part because loss functions can be anything, and you can think of it as like a teacher, right? It kind of tells you what you want. It tells you what you're looking for. And I mean, the thing is, music is subjective, so there's not one thing we're looking for. There could be a number of things we could look for. We could try to match up the notes as close together in pitch space as possible, or we could actually try to match together the intervals between notes as close as possible. So the difference is like, you can think of it this way. So if I have like a note A, B, C, like that, it might match closely enough to A sharp, B sharp, we'll say C sharp, right? Because these are only a semitone apart, right? And that's one way to think about matching things up, is keeping the notes as close together as possible. But there's another way to think about it, which is intervals, right? So if I think about A, B, C, actually, let's do this. Let's say it's like A, B sharp, and then B. Does that make sense? Yes. Okay. So you can see each one of these is only a semitone away, which is as close as you can get without being the same note, right? So that would seem good from one loss function's perspective, which is how far apart are these two notes on the piano. But it's actually maybe not the best option, because if I play this, it's going to be A, B, C, but here it's going to be A sharp, B sharp, B. It's going to go down a step here from B sharp to B, right? And you can see that the direction that this phrase goes, or this little musical motif goes, is it goes up. A, B, C goes up on the keyboard, right? So we might want to preserve that, which means maybe we want to preserve the intervals or the distance between each pair of notes. So from A to B is a tone up, and B to C is a semitone up. So if we copy that, we could, for example, do C, D, E flat. And what that means is basically C to D is the same distance as A to B, even though they're totally different notes, right? They're quite a bit further apart on the piano. Like they're like about, sorry, that far apart, whereas a semitone's this far apart, right? So this is bit further apart, but what matters is the distance between the adjacent notes is exactly the same between this thing and that thing. So this is by interval. So we'll call this by note, loss function, by pitch, and then we have loss function by interval. So you can see that these are two different answers, and which one we prefer kind of depends on what we want out of the music as a composer. And so it's not something you can prove will be better one way or another. We kind of have to just try it. And I imagine there will be a lot of tweaking of this loss function to make it do exactly what we want, right? There's one other problem here, which is if we go back to the setup, we need to split this thing up into 12-note chunks, right? So we have some music, we're going to turn it into a serial 12-tone piece. To do that, we need to cut it up into these 12-note chunks to do the permuting. Well, it doesn't matter where you cut up the chunks, because let's say, so into chunks. Let's say I split like A, B, C, and then there's a split here, and then it's going to be D, E, F, something like that, right? So here's my split. Well, let's say in another case, I put my split here. Here. Okay, let's change up the notes a bit to make this a little more obvious. Let's say my original music was like this. C, D, C, D, and then D, E. So you can see that there's a repeat here, right? And in this other example, I split the music here. So in the first case, I split between the two Ds. Now what that means is when I try to 12-tone this, I can actually repeat the D between these two chunks because they belong to different chunks, right? So in each 12-note chunk, you can only use that D once. But because these two chunks are in two separate 12-note sections, you can start the next 12 notes on D again, right? Because it just restarted. You just finished the last 12 notes, and now you can do it again. But here you can't, because this 12-note chunk can only have one D in it, right? So you can see these will give different results if we want repeated notes. And actually, the original composers, like Arnold Schönberg, did this on purpose. They would write to a certain point in order to have these 12-note chunks align up, and then they could use the same note twice. So you get two of the same note for a very special occasion. So I think what I'm going to do here is probably try a bunch of different splits. And also, there's also the question of how do you split chords? So sometimes multiple notes happen at the same time, right? And obviously, it's like, okay, well, what if I've already had, what if I have a 13-note chord, right? Which note gets to belong in the next 12-note chunk, right? It's not exactly obvious how you're going to split those, right? Right. So obviously, serialism is not really just a recipe. There's an artistic side to it, which is making these kinds of decisions. And, sometimes Schönberg and those guys in the Second Viennese School, they would break their own rules because why not? You're making music, it's not a theorem. You can break whatever you want, right? It's just the guideline in the end. So that's not something we can program this kind of deterministic state machine to do. Although you could probably train a neural network to kind of make more 12-tone music. Although who wants to do that? I don't know who would want to do that, but yeah, it is in principle possible to do that. What we're going to do is something simpler, which is we're just going to follow the rules and turn something that's perfectly good music into something that's perfectly nasty 12-tone, atonal nonsense. Okay, so that's the plan. So we are done the Y. we are going to move on. So now we need to start doing some programming. And I have some MIDI files, and I'm going to try to get them into Python and manipulate them first. That's step one. So let's do that. So here's my shell, my Windows subsystem for Linux. And the first thing we're going to do is we need to install some Python libraries that can do MIDI manipulation. And I did look this up. So let's pull up a tab for this. There we go. Oh, there it is. That's even better. Okay, so there is a library, a Python library called MIDI, and I just found it today. We will see whether it works well or not. I have no idea if it works. So I'm going to create a virtual environment and install MIDI for Python. So what that means is I just need a container that will do the installations for me. So the idea is I don't like to have all my Python things installed, at the same time. They can conflict. Instead, I will create a container and kind of isolate out each project's installed libraries so they don't mess with each other. Let's do that. Virtual env. So here's the command to create a new container. And then we want it to be Python 3 because I don't use Python 2 anymore. It's just older. And we're going to put it under our home folder in env and Schönberger. I don't know why I called this project Schönberger. It just is. But now we're going to activate it. So what that means is we are using this version of Python with whatever's installed in this virtual environment. And when we're done, it's not going to infect and leak into everything else that I do. Okay, so far so good. Now we should upgrade pip. Pip is the Python installer for packages. Upgrade that. Now we can pip install MIDI. Okay, and because I already tried it earlier, it's already cached, so that was quick. Let's test it out. Python import MIDI. Okay, and now what we should try is loading up a MIDI file. So let's look for a MIDI file here. I have a couple. Okay, let's start with something short. I have a test scale. That's the shortest one I have. I'm going to copy that into in Schönberger. Oh, hey, what do you know? It's already there. I'm prepared. So let's open that up. So apparently the way you do that is we need MIDI file. So MIDI.MIDI file. And now we are going to import test scale.mid. Oh, I can't find it because it's in the wrong directory. Okay, let's change that. Schönberger MIDI. Okay, that should be better. Yeah, okay, there it is. So let's save that to a variable so we can look at it. We'll just call it MIDI file. MIDI. Okay. And if I type out, MIDI, you can see there's a whole bunch of stuff. So what is in a MIDI file exactly? Let's see, there's some kind of metadata at the beginning. It tells you like how fast it goes, how to split up time in this file, names, stuff like that. Let's see, we have a key signature, we have the tempo, and then we have some control changes. I actually don't know what the control changes are. Maybe they're to control volume overall. Okay, the important thing is once you get here, right, these messages that are note-ons, those are actual notes that the MIDI file plays. And in case you don't know what a MIDI file is just a way to save notes in an interchangeable format. So like if I play on a piano like this, right, then I can record that digitally, like if I'm playing on an electric piano, right? And basically the MIDI format will save when you hit the keys, which keys you hit, and when you release the keys, and how loudly, how hard you hit them. So what do we have here? We have note on. That means, it's a note event. We have a channel that's like which instrument it came from. We have the note, which is the pitch of the note, and these numbers correspond to letters, right? Like C or C sharp, right? These are the notes, and in specific octaves. So it's not just like a C anywhere on the piano because there's multiple. It is like maybe middle C in this case. Actually, I'm pretty sure 60 is the middle C in this case. Okay, last thing is velocity. That's how hard you hit it, right? So on a piano, it's like how fast you press it down, which makes it louder if you go faster. And this is when, so time 0, and this is probably in milliseconds or something, right? And then what else do you have? Velocity 0, that means the note is done, right? This releases the note, and that tells you like how long it takes. Yeah, so that's basically all the notes we care about. And today, as we are kind of doing all the note manipulation, this is the kind of thing we're going to change, basically. We're not going to change any of the timing. We are going to change the note pitch. Okay, so far so good. We have a MIDI file. Next, what we need to do is kind of go over these messages. And basically, we only care about the note messages, right? So far, it's giving you a way to iterate over all the notes in the MIDI file and find the meta messages. That's not what we want. Let's just try iterating over that. So for message in MIDI. If message dot, let's see. Actually, let's just see what a message looks like. So we're just gonna write dear message, which just lists what the message can do, and then we're gonna break, which just stops the for loop early. Okay, so you can see in a message we have let's see, bin. I don't know what bin does. Bytes copy dict from dict hex. Is meta is real time. I wonder if real time is the one we want for note messages. Let's try it. For message MIDI, if message is real time, we'll just print it. Oh, sorry. That is not a function. Is real time is a property. Okay. So there are no real-time messages. Great. So maybe we'll try this. If message is meta, but not. If it's not this, then we'll print it. Okay. Yeah, okay. Now we are almost getting all the things. Except we also have these control changes, which we don't care about. So maybe we should do something about that. Let's go back up. So looking at these properties, we have name, the name of the event, the time of the event, the type of the event. We should also have some other things like the velocity and the channel and the note. Those must be in the dictionary here. That's my guess. Okay, so we're going to basically look for note on messages and go from there, I think. Okay, so let's try this again. In fact, let's just pull out the first message in this MIDI file, right? So if I go for message in MIDI, first, we'll just call it note equals message and then break. That'll give us the first note here. It's not the easiest way to do this, but that is not a note we care about. What we want is the actual audible notes. So let's change that up to be the last note. And we can just run this loop again. It'll just keep iterating until the end, and that will give us the last note. Oh, that's the end of track. Okay, so we don't want that either. Okay, I'm gonna need a slightly different machinery for this, which is just MIDI. Let's try this. Okay, there we go. So I just needed an iterator over that and pull out, something in the middle of this, right? Okay, so let's see. This note is, let's see, it's got a message, it's got this. We just need to know what is what in here. And I could read the docs, but That's no fun, right? What programmer reads the documentation when they can mess around with things blindly? So let's see. We have note.note. Okay, that gives us the looks like that gives us the pitch. Note.time. Okay, that's the length of this event in time. Note.type. Note on. Okay, and note.velocity. 0. Okay, that's great. That's kind of the information we need. Remember, we're mostly just concerned with this note property here because that's the pitch. So the next step is we need to get everything that's a note on event with a non-zero velocity. I think that will be all the numbers, all the pitches that are actually sounding in the piece. So let's actually pull up a proper code editor now. I'm going to pull up VS Code. That is my editor of choice. I'm not trained in computer science, formally. So if I come across as a bit of a computer incompetent, it's because I don't have that training, or at least that's the excuse I tell myself, right? So that's why I use simple tools like VS Code and Ubuntu instead of more complicated stuff like Emacs and Arch or something. I mean, who even uses Emacs anymore? I think Vim or Vi have one these days. The editor wars have seemed to faded away over time. Anyway, okay, so I'm just gonna open up the folder with project. Oh, it's already open. Excellent. There are no files right now, except those MIDI test files. This is the one we just opened. Okay, so we don't care about that. Let's create a new Python file, and we'll just call that. We'll type it this way, because that's how I spelled it. Okay. Technically, there's those 2 dots above the O, but yeah, I'm not typing that into my editor. That's a great way for your computer to complain. It's unfortunate that ASCII has such a hold on, programming, but that's kind of how it is. Programming is really English, Anglo-centric, Okay, so we're gonna import Mido, not whatever that was. And actually, while we're at it, let's set our Python interpreter. Select interpreter, and we're just gonna select the one we were just using, which is well, it's pretty close to this one, so except it's not. Okay, I'm just gonna type it out. Why did that not work? Okay, I need to maybe exit out of here and just check where everything is, because sometimes I lose things. There it is. And it should be under bin Python 3. Yeah, that's where I want to go. So I'm just going to copy this. Control C. Yeah, on my usual terminal in Linux, it's Control Shift C. So sometimes I hit the wrong buttons. Okay. What? A little weird. Yeah, this is my lack of computer science showing, I guess. Okay, I think that is correct, right? That's really weird. Okay, you know what? It is what it is. No, I really need this interpreter because I installed Mido into it. Classic. Yeah, this is where I want, right? Okay, yeah, that's fine, right? Okay, I think I got it. Yeah, okay, finally. Sometimes it's a little weird. Okay, and I'm gonna install MyPy because It's just a way to check my code before I run it, check for bugs, and goodness knows there will be bugs, many bugs. So it's probably best to do that. Okay, so now what we were doing is we want to first get all the notes are sounding in the piece. So what that means is velocity greater than 0, and let's see, they have to be note on events. Right. I think that will be it. If we end up getting the wrong things, we'll filter for that, right? So let's create a function to do that. It will, let's see, we'll say get sounding notes, and it will take in a MIDI object of type, probably a MIDI file. Probably. It's hard to say. Maybe that will change. But anyway, for event in MIDI, we are going to basically say if event dot was it name? No, type. If event dot type equals note on, that's the first part, right? We need note on events, and we need velocity greater than 0. So and event dot velocity greater than 0. Then we are going to save it. So we need somewhere to save that too. Let's create an array. We'll call this notes. And notes.append, we are going to add in this event. And then once we're done all that, we're going to return the whole damn thing. Yes, notes. Okay, that's that. Okay, and let's give it a shot. So if name equals main, we're just going to create some boilerplate to run this. Run. Name equals main. We are first going to load a file, right? So we need a file name. Let's hard code it for now. We can change that later. Test scale.mid, and it is under MIDI. We'll call this MIDI. And then we are going to get sounding notes of MIDI. Okay, and the last step is, let's just print out the notes to see if that works. Okay, so that's our little program, our tiny little program. Let's give it a run. So to run things, let's, I'll run it in this window so it's a little more easy to see. So you can see I am in the Schönberger Python environment. That's what that means. I am in the wrong directory, so let's go to where our code is. Yeah, so here's the MIDI files in a directory. Here is the code, and we're going to try running it. So Python Schönberger. Okay, hey, look at that. Did we get all the notes? Well, to figure that out, let's print it slightly differently. Let's add in a new line after every note, so I can actually tell them apart. Is that better? Is that better? No, it's not, because there is only one thing in this array. Huh. What? So that's interesting. Why would it not? So notes should be an array here, and we return an array, and then this star means I split up the array into its constituent parts, and I should print after every part this new line symbol. So I did that, right? So here there was an array, and here there is not, but unfortunately I still have a bunch of nonsense. Interesting. Well, let's just try printing one of them. Okay. I don't know why the star notation didn't work there. That was interesting, but you can see that iterating over this array that I return, that's fine. So now I have all these notes. And I'm just gonna make sure this is actually the music that it's supposed to be. And for that, I'm gonna open up, oh, sorry. Right, no, this is fine. So this is just a music notation program. And this is the MIDI file. So it should go like this. It should go up and then down. And it starts on C. If you can't read music, that's a C. That's also a C. It's just higher. And it just goes up one letter at a time. Let's just make sure that's happening over here. Oops. Okay, so first note. Let's clear this and do it again. Okay, so first note is 60, middle C. Okay, the last note should also be 60. Very good. And then it goes up 2, 4, 1 step for the E to F transition. So C, D, E, F. There is the semitone or the smaller step. G, A, B, C. There's another semitone. Good. And then it repeats the note, goes back down, I think. Let's see. Yeah, it repeats the note here. Here to here. And then it goes back down. Excellent. Yeah, that looks good. So I've gotten all the notes now. Very nice. Okay, next, we need to be able to mess around with the pitches. So let's try that. Let's try editing one of these pitches and saving out to something else. So I'm going to just kind of write out a stub of what I would like to see here, which is something like this. We're going to change the note somehow. Let's call that 12 tone. Let's say map to 12 tone. Notes. And then, there is a problem here, which is we don't want to mess with the structure of the original MIDI file. We really just want to go through the notes, change their pitches, but keep everything else the same. So maybe a better way to do this is to iterate over the sounding notes. Right now, get is giving you a brand new array with just the notes that you care about. But instead, maybe we want to access each of these note objects kind of in place. So I'm going to try something. If these notes are actually, like if each of these MIDI events is a like object, right? We just need a reference to each one of them to change them. Now, I could do it this way, but I could also use the yield method, which goes like this. So what that means is this is now instead of an array, it's an iterator, which means it just like goes through something and gives you stuff as it goes. And the thing it gives you is these events, right? And let's change the name too. Okay, great. So now, of course, we can't save out the notes as the iterator, but we can run this kind of map to 12 tones function to generate new MIDI, and then we're going to save it out somehow. Okay, we'll figure out how to do that in a moment. Let's create the missing function, which is def map to 12 tones, and we just need a file, really. I'm just including type annotations because I guess I'm used to it. These type annotations, they don't do anything in the code. They just warn you if you're putting the wrong things in the wrong places. Python is famously dynamically typed. Well, not really. I should say it's duck typed, right? So you get what is it? The types are decided for you by the computer unless you specify otherwise. So yeah, that can cause bugs sometimes where you think you're working with integers, but actually you're not, because the computer didn't realize you were. So yeah, it can help to avoid those errors if you specify exactly what types you want to see in a given place. Yeah, but it doesn't change how anything runs. So the idea is then we're gonna do something like for note in iterate over these notes, do something to the notes. And we're not doing anything right now, so I'm just gonna write a pass in, just make sure everything works, right? So let's see, we need MIDI here, and we need to save it out. So now it's time to pull up the documentation, and let's clean this up a bit. Okay. What do we have? Opening a file, iterating over messages, creating a new file. That's what we want. So let's see. Looks like you need to create a new track and then save. Okay. So let's try that. We're gonna create a MIDI file. Actually, that probably should happen in here, right? So let's do that. And I'm using this this MIDI file object so much, I'm just gonna import it. So I don't need to write out mido.MIDI file every time. Now I can just write MIDI file. That's a lot simpler, right? Okay, so so far so good. I'm gonna take a drink. And I wonder how loud this is. Yeah, my voice is still reasonably loud here. Hopefully I haven't been mumbling. Okay, turned it up a hair. Maybe a hair more because I'm pretty far from the mic. Yeah. Okay. So, where are we? We've got this map function, which gives you a new MIDI file, and then we just need to save it. So, and again, we're going to hard code the location just because. Like that. Okay, great. So we did that. Now we need to go into this 12-tone thing and do the magic, right? So the first thing we're going to do is just try to save out the same file. So to do that, we can just return it. So right now it does nothing, just like me in high school. So let's give it a shot. Well, I should say just like me in high school when, according to my parents, right? But anyway, looks like there's a little error here. Why would that be undefined? What is the problem? Got it right. Oh, I spelt it wrong. Map to 12 tones, not map to 12 tone. Yeah, let's call it that. Oh, yes, and we need this directory out, right? Let's just create that. Make dir out. Okay, let's try that again. Okay, I think it worked. Let's see. Yes, okay. And this test scale should be the exact same file, so let's just, you know what, I'm just gonna trust that it is, because we want to do stuff to the notes now, right? So let's do that right here. If it is a note, let's change the note's velocity. No, sorry, not the velocity, the pitch, right? So we're going to say note.note. Let's print it out just to make sure we've got the right thing. And then we're going, let's just set them all to 0 or something. We'll just set them to something unassuming, like middle C, 60. Okay. And let's see if that works. So we're gonna run this again. You can see those are the notes, those were the notes, and now they should be different once we open up the other file. So let's try that. Let's see. So here's the test scale as it sounds originally. I'm just gonna pause the music. I don't know if that's loud enough. Okay, but you get the idea. That's a simple scale. Now, if I go to out, okay, that didn't change the notes at all. So that is clearly the wrong way to change the notes because it did not save out different notes. And just to double check that, I'm just going to try iterate over notes of the new MIDI and just print everything. That's unfortunate. I thought that would work, but clearly it doesn't work. Oh, sorry. I need to actually iterate over it. Easiest way to do that is like this. Yeah, okay, so you can see the notes are definitely not all set to 60. That is a problem. So let's go back to the documentation for once and actually figure out why that's happening. Okay, I'm just gonna clear that and move this to here. Okay. Okay, I'm iterating over messages. Yeah. Time, I don't care about time. I only care about pitches. So let's see if the docs say anything about changing the pitch. So MIDI's pretty complicated. It's not just a way to record like the notes in a piece. It's also things like how do physical instruments communicate. In fact, you can use MIDI live. Like you can have a keyboard sending you messages about notes on and off, and they will be played by something else, like a synthesizer in real time. So it's kind of a pretty low level thing. It's kind of like if we were working with like packets instead of IP, you know, like from a networking standpoint, you know, you're working with Ethernet, you know, and not something else. So I'm just gonna search note parsing MIDI bytes. Yeah. Messages. To create a new message, you can set. So in theory, you can set these things, right? So in theory, I should have set this note. It's just it's not saving in the grander file, the grander scheme of things, right? Let's try that. Let's see if that's the case. No. Okay, that's interesting. Oh, yeah, it is. Okay. It is setting the notes to 60. So that's not the issue. The problem is that the MIDI file does not see this, even though I changed the individual note objects. Okay. You can make a copy of things. Okay. So this is the important thing, right? This is why we read the docs clearly. It says that MIDI always copies a message instead of modifying it in place. So in theory, these messages are immutable. Okay, interesting. So what that means is every time I change the note here, it's making a new copy, so the original doesn't get changed. What I really want then is to somehow like replace that note. Right? Maybe the way to do it is I'm going to create a new MIDI file in here and just add every event into it, right? And basically, as I'm going, if it is a note, I'm going to apply some transformation to that note. But otherwise, I'll just throw in the other events into this new MIDI file. And that way I should, in theory, end up with the exact same file, hopefully. So let's give that a shot. Messages. How do I copy a message again? Copy. Message.copy. Okay. And you can also create a new. Okay, so looks like what we need to do is something like this. So the plan is we need to go through all the messages because we're creating a new MIDI file. We need to include everything from the old one. If it's a note, we need to do something to it. Otherwise, we're just going to copy it over to the new MIDI file. Right? And now the problem is we can't just do this one note at a time because the permutation algorithm requires 12 note chunks. So basically what that means is we need to have some kind of buffer in which we're storing all the notes. In fact, let's just store all the notes at once and then reconstruct the file later somehow. Okay, so how to do that? Let's see. We have some kind of note buffer. So maybe the way to do it is we're going to have a list of some kind of all the messages, and the notes will be in that list, and then we will use some filter to go through the notes in that list. We will change the notes as much as we like, and then afterwards we'll take that list and make a new MIDI file from that list. Okay, that's the plan. And I'm just going to check to see how you can add a message back into a MIDI file. This is all about messages. There must be a way to stick them back into a file. Let's go back to the file section. Here, creating a new file. Here. So it looks like you have to create a file, a track, and then append, append, append. Okay. So I wonder if you need the track, you know. Is that optional? Is that required? Who knows? Okay, let's just give it a shot here. So we were first going to create a so iterate over all messages. Message is note. So we're going to change this recipe a bit. We're going to copy all messages into array. Change the notes in the array, and then write out all messages in array to new MIDI file. That's the plan. Okay, cool. So step one, copy it all, right? So for event message, let's say in MIDI, let's do it in the shorthand form in Python. You can do this in one line as, let's see. Let's turn the music back on. Yeah, that's nice. Okay, so let's see. I just want the message. Yes. Okay, so there's our array. Okay, now we are going to iterate over notes of this message array. And the nice thing is here, this can actually just be any iterable of let's import message. So I'm just adding type annotations again. So what this means is I don't care what messages are stored in, so long as it's something that I can iterate over, like a list. So it's an iterable containing messages. Like that. Okay. So that doesn't change, right? This code still works. That's the advantage of duck typing, right? It just kind of works as long as the type allows these kinds of operations. So now I'm iterating over the notes to do something. So we're going to do the same thing. We are going to change every note pitch to 60. and we can get rid of that. And then we need to create a new MIDI file. So let's go over the documentation. Let's just copy it straight over, right? This is basically what we're doing. So we create a new MIDI file. We'll call this new. We create a track. Add that track. Oh, we need to import that. Really? Oh, it's because this library, MIDI, doesn't have some kind of documentation that allows VS Code to automatically pull some hints for importing things, right? So I'm just manually adding the import. So now I have this, and let's see. I have the track in the new MIDI file, and I'm going to have to append our new messages. So we've already got everything in our message array, right? So we don't need to specify a specific message. We just need to go through them all in order. So let's do that. And again, I'm just using the one-line shorthand for Python, although it's kind of ugly here because we're not saving this to a variable. So maybe I should just do it this way. That's a little neater. Okay, and we need to return the new file, not the old one. Okay, let's give it a shot. Message time must be int. Well, that's a problem. So it looks like it was doing okay for a while. Something's getting printed. Oh, so this thing's printed. Interesting. So it must have gotten to this print statement down here. But somehow, I just realized my face is starting to cut off the text here. So let's switch the order there. Okay. So that's interesting because it looks like it got to the print statement here. But something happened when it tried to save it. Okay, so let's look through the print statement and see what's actually in this space. We have note on 60 and note on 62. So that's a problem because we're supposed to have the exact same thing. Oh, I forgot. That's why. So when I change this, right, I need to actually change it in this array, right? So we need to switch up how we do this. Because now every time you go through this array, you actually need to like change the object in the array. You know, this is very unPythonic, but like it's not how you normally do it in Python. But let's just do it this way, which is we're just gonna say for I message in enumerate message array. Now, the reason why I'm doing this is so that I can access the message array using this index I. And that way I can change whatever I want in this array in the same location as the message. So now it's going to look something like this. If the message is something is note, then this message array at I is going to equal a new note, which is going to be the one we manipulate, right? And let's just create a placeholder function to do the manipulation. Actually, no, we're going to come back to it. So let's just leave it that way. Note.note equals 60. Oh, right. So this change here, this change should return a new object because that's what they said it does automatically. But just to be clear, just to be like extra clear, right, I need to copy all these messages too. That's the part I forgot. Okay, so now I can do something like, yeah, this is probably a copy again, but that's fine. I'm setting it, let's just make it explicit, right? So we copy the message, change the note, and then we stick it back into the array. Okay, now we need to change this. So we're no longer using this iterator. We just need to know whether a message is the right kind of note. So let's do that. That is the condition, right? The type is note on and the velocity is larger than 0. Okay, there we go. Okay. Let's clean things up a bit. I know there are things like black, Python black, which will prettify your source code, automatically format it, but I seem to do things manually a lot. It's just a habit. I used to write Java code in high school, and it just got drilled into me. You gotta put spaces between your operators, and how close each bracket nicely, and line things up. Actually, it's really easy to transition to Python when you're already writing neat code in something like Java, right? Anyway, back to this. We have a new MIDI. There's an error here for some reason. Oh, did I miss an indent? Where exactly did I miss an indent? Oh, it's fine. Okay. It's fine. Okay. Okay, it's still having an error, but let's at least see if it's getting the right stuff out. So I'm just gonna print new MIDI. Okay. Huh. Those are still not the right notes. You can see the notes are changing. I'm just gonna see, are these messages really changing? Hello? Hello? Yeah, this is my non-computer science print debugging happening here. And I don't want to print this anymore. Okay, so let's see what's going on here. Oops. There we go. So when the first thing that prints is this, right? And you can see those are the correct notes. Those are absolutely the correct notes. Now, the next thing that prints is the whole array. And those are not the correct notes. That's very strange, to be honest. Why would that be? That's very strange. This is the danger of using some software library you've never used before. You'll be stuck debugging because you just don't understand what's going on, and I'm sure somebody who's used this before will be laughing at me because it's so obvious. But that's how it is sometimes. So print message array. Am I editing the array correctly? So what's very strange is that the message array is all correct here. Right? When I print this out, I'm going to print out the whole array as I go and see if that's happening. Notes. Yeah, those are not the right notes. You know what? Let's change this also to something that's easier to spot. Okay, it did change a note here. You can see that's the correct note. How many of those are there? They are all that, I think. Yeah, so this is fine. Huh. Okay. fine in here. Let's print it after. Yep, that's still the correct note. Interesting. Okay, that's a little weird. Oh, I see what's happening. So the note, I was ignoring all the velocity 0 objects, right? Those mean note off, but you can see that they do matter here. That's what was tripping me up. So when the note's on, sure, you have the correct note, but when the note's off, you need to be turning off the same note. So each note is actually a pair of messages. And to make that clear, let's print out the original MIDI file here. Yeah, this, you know, back in the day when I was doing my first undergrad, I did work with MIDI files to some extent, just enough that like I had like programmatically messed with them a bit, and I would have been able to tell you this. You know, I would have been like, of course, every MIDI event, every MIDI message has 2 parts when you're playing notes, because it has to turn the note on and then back off, right? So you can see that here, right? It's on first and then off, and the velocity 0 is the off part. So actually we need to be iterating over this and looking for pairs of messages and pairing up the ons with the offs. That's a little bit trickier, but we can definitely do that. So it's not as simple as saying this is a note. Now we need to kind of return note pairs. So what's the easiest way to do this? Because we still want to preserve this kind of message array here, right? We don't want to put the messages out of order in case it messes up the MIDI file. I don't actually know if the MIDI file requires the messages to be in a certain order. I'm pretty sure it does, because these times are relative, right? These times are not absolute. So if you switch things out of order, they're going to happen at the wrong time. So let's think. The problem I'm facing here is that notes can kind of happen in weird overlapping ways. So if I show you, where's my slides? Here they are. Sorry. There they are. Okay. I go back to my slides. Here's the issue I'm facing. Say I've got note 0 here. Give it a nice orange color. Now, if I have note 1, which looks like this. Now, let's say this is a D, and this is a B below it, right? You can see that D starts first, so D is going to have a note on event here. Let's give it a white color. Okay, so this is note on. Right. And here's the note off. But the problem is B is also going to have a note on that comes after, right? And then its note off happens before. So it's not as simple as just iterating over this array, because this array is going to have on, off, off. And what we want to do is pair up this on with this off, and then these two on and offs together, right? So you can think that maybe what we do is you take this array of events, and what you want is a reference to the messages that belong together, like these two. And the way I'm thinking of doing that, let's move that away, is let's do it this way. We're going to have references. So this array is going to refer to a bunch of things. And then we need a kind of abstraction that points to the right places in this array. So let's create an object, which we'll call a note. And this note needs an array of events, messages. Okay, and we also need its start message and its end stop message. Okay, and then we'll maybe have some helpers to kind of let you do things with this note. But let's start by doing that. So we're going to initialize it. And what we need is the source, which is some kind of array of messages. Okay, I shouldn't have removed this import because we need it back. And also we need, what do we need here? Wow, brain fart. Yeah, the problem with playing music in the background is I normally don't listen to music, so sometimes it like hijacks my brain and then I can't think for a moment. It's like being hacked, you know? This is the kind of weakness of studying music, is then you can't listen to music as a background thing anymore. At least I can't. It just distracts me too much. Yeah, I've got some good stories about that, like, you know, driving a road trip with my wife for like days, complete silence. We don't play music in the car, at least when both of us are in the car, mostly because of me, because I can't drive with music on. But don't worry, we talk. It's not like it's complete silence, you know, for 12 hours. That would be terrible. So let's jump back into this. We have our source. We have, we need our start and end. And we're just gonna use indexes. Right? So it's just pointing to different places in this source. Okay. And real quick, start and okay. And one more thing, let's just do some sanity checks. So we never want the start to be less than 0. Of course, and greater less than length of source, right? So you can't have events that are outside of the source. We also need to make sure that we have the right messages, right? So the message should be the start message should be let's see, it should have velocity greater than 0, and it should be a note on thing. So we want this, right? So now we can bring this previous function into the note class, and we'll say note on, and also is note off. And the only difference is that the note off event has a velocity of 0. Great. Okay. Awesome. And now we can just check that source start has to be is note on, and source end is note off. And we'll call that another assertion. We'll stick those right at the top so we don't miss them. Okay. There. Lovely. So what we've done is we make sure that the start and end are valid note on and note off events. We save it all, and then we have some helper functions that do things. Oh, and don't forget, now that it's in an object, we need a self argument. And you know, I don't know much about Python's details, but I do know that the self thing is like it's like this in JavaScript, right? It's something that refers to the class, the object that is instantiated from this class, and you need to include it in anything that is part of the object. You know, like a method in Java, you would call that, right? These are methods of this object. Okay, so far so good. We'll add one more convenient function, which is def change. We'll set pitch say pitch is an int, and this will just be a helper that does this nonsense down here, right? So message equals, now we pull it from the array, which is self.source at our start. Actually, there are two, right? There are two messages we need to change. We need to change the start and the end message, right? So let's create a helper function for that. We'll just call it the same thing. Index. Okay, so this underscore just means it's private. There's no private functions or methods in Python, so we fake them with these underscores. In Java, you basically cannot see these unless, like if you're programming, right, and somebody else has a private function in their library, you can't see it unless you do some like decompiling or inspection. Yeah, in Python, it's just like, please don't look here. Don't break our code. So let's see. In this case, we just want to make this a generic move so we can call it twice in this actual function here, or method here. So at this index, you're going to copy the thing at the index, set the pitch to the new pitch, and then save it out. And so basically, you're going to change what's in the source array, right? And that would be in the same index. Change it back to this message, which we've changed. Okay, now we just need to call this twice, once on the start and once on the end. Self. Right, self because it's a method, not a function. And the self gets filled in automatically by Python. We need a pitch and an index. So the pitch is from this function call, but the index is going to be self.start and also self.end. We need to change both of those messages. Okay, that should work. Let's see if it actually does work. So 12 tone. Oh, quick stretch before I try this. 12 tone. We are going to, we have this array. Then we're going to create a note object for every thing that's a note in this array, I think. Okay, this is going to be a little tricky because now we have to search through the array and find everything that's a note. And maybe the best way to do this is kind of greedy. We are going to iterate through every message, and then if it is a note start, we're going to store it in some buffer and keep iterating until we see a note end on the same pitch. And then we're going to assume those note starts and ends are they belong together. If they're on the same pitch, we just assume they belong together. And that's that, basically. So let's create a new function to do that. Let's def get notes. Yeah, we'll make this iterable of messages. It's going to return. Oh, I forgot to annotate my returns. Yeah, that would be nice. Not very important, right? It doesn't change the function of anything. It just gives you a little better idea of what's happening in your code when you tell the reader what's happening, what each method or function returns. So this doesn't return anything because it just sets it internally. Same with that. Okay. Cool. So now get notes is going to basically return a bunch of notes. So like that. And to do that, like I said, we're going to iterate over messages. If the message is a note start, add to some buffer. Message is note end. Going to match it up. Let's say match it up with the first thing. So the earliest note in buffer, which is the same pitch. Okay. Something like that, right? And also raise an error if we have any note start without a note end, or vice versa. Okay. Great. Let's code. I drink first. Yeah, I tried the test stream without water. That was a disaster on my throat. Don't do that. If you value your voice, make sure to stay hydrated. You know, I learned that through singing, right? So I sing in a choir, and yeah, it's very important when you're singing. You know, this is your instrument. You gotta take good care of it. You know, one other way I should take care of this instrument is to really speak from the diaphragm. That's like using your breath to produce sound instead of forcing it out through your tightness in your throat. So yeah, that's kind of a work in progress. We'll keep working on that one. Let's do this. We need a buffer, and we'll just keep it simple. We'll just use arrays. Right, and for message in messages, actually, let's create two buffers. It might be easier to do it that way. So the reason why I'm thinking this way is at the end, we need to raise an error if we have some missing ones. And it's easier if you just have two things that you're just gonna like pull out stuff from, right? Is it though? Maybe not. We'll just stick with this. I mean, it'll work. It's not efficient, right? Like I said, I'm not a computer scientist. This is going to be a pretty bad runtime, but that's okay because, you know, these days with computers, anything less than in like a million operations, you can basically just like don't worry about optimizing it, right? Like run an O to the n, cubed algorithm. Just do it. Like it's only going to be an issue when n is big, right? And usually with modern computers, if you've got like n less than, like after you calculate whatever's in the big O notation, if that number comes out to less than 1 billion, you're usually okay with like a modern computer. Like laptop, big computer, it doesn't matter. I've run things for like an hour or two, just, you know, and it's done. It's like, it's easier than optimizing for programmer time, right? Again, maybe this is my non-computer science speaking, but that's how I roll. So the idea is we're just gonna fill up these two buffers and then search through it from the start and like pull out the notes when we find matches. Okay. Yeah. So really linked lists is what we need here. But again, we're gonna let Python take care of the array handling. We're just leaving it, you know, to Python to be its inefficient self, right? This is why I don't program games, apparently, because I don't know how to program for performance. The important thing, though, in research is programming for, you know, like getting things done. Right? So that's kind of a work in progress too. We're going to let's see, we need these two functions. right? Is node on, is node off. So let's just change these to static functions. What that means is we can access them without having an object of this class. It's not like it needs to know anything about the object, right? So we can get rid of that self part again. And we can leave that because even though it's a static method, you can call it two ways. You can call it through the note class, or you can call it through the a specific note object, right? So that's fine. Okay, so now we are going to here, and we're using the class to call isNote on and off, right? IsNote on, then we need to append it to this is start buffer. Okay, and same thing with off, right? So we'll just change that. Okay. Great. Last step is we're going to create the notes. So we'll move this down here. You know, we just did that, so we can erase the comments because this code is pretty self-explanatory, right? Okay, so now we need to go through all these messages in these buffers, and basically, okay, we'll start from the start buffer. So for note in start buffer, we're going to find an end in the end buffer, which is the same, right? And then we are going to match it up and create a note from that, right? So again, it's not efficient, but it will work. Just gonna iterate through it, so it's O to n squared already. But this will terminate early, because as soon as we find an end, we're going to leave. So the average case performance is not terrible, right? So if it's gonna be like if this end dot, we need the pitch, right? So that's this property. If end dot note equals start dot note, then we're going to create a new note. Source iterable. So our source is our messages, our start is our current start position, and our end is our current end position. So we do need to know where these things came from. Okay, so we need to enumerate over messages, because we need to know the index of the array, the index from the array where it came from. Right? So I mean, I could store that all in the start buffer. I'm thinking, is there a more efficient way to do that? You know what? We'll keep it simple. We'll store everything. Again, inefficient, but you know, when you have like what, 16 gigabytes of RAM to play with, 32 gigabytes of RAM, it's like, whatever. Who cares if I'm using an extra byte here or there? You know, like. Sometimes I just save out, you know, all of the intermediate activations of a neural network for like 10,000 examples right into RAM, no problem. Yeah. Now in genetics, like a lot of computational genetics, you actually need even more RAM than that. You might need like 100 gigabytes of RAM to do something, and then it still won't be enough. So then you need memory mapping. Yeah, that's a whole different ballgame. But this is fine. You know, like we're not working with like matrices that have like 10 million dimensions or something ridiculous like that, right? Okay. Sorry, I'm just gonna pause for a moment and check my stream. Still running? Excellent. Okay, we are appending this note, and we need our start position and end position, so we will call this I. We'll call this J. And what's happening here is Python's automatically unboxing this tuple that we gave it earlier here. Right? we have our numbers. So now our start position is I, and our end position is J. Right, and now we need to remove this guy from the buffer. So how do we do that? Well, an easy way to do that is, actually, there is a way in Python, right? You can just straight up pull something from an array. Python remove from array. Yeah, like, I mean, I've never formally trained on Python, so I still forget basic things. Probably, let's just delete by index, I think. Delete and pop. Okay, those are the two ways. Okay, cool. Now, the annoying thing about that is I have to enumerate this as well to get the index. So, you know, whatever. Let's just do it. This is starting to look a little ridiculous, but and very un-Pythonic, but that's okay. At least we're getting it done. So now we can end buffer. That should get rid of that. Okay, cool. Now, if it can't find anything, right, we need to raise two errors. One is if we have anything left in the end buffer after we're done, right? Let's call it runtime error. The most generic error of all errors. If the end buffer missing starts, we'll call it orphan ends. And then we'll just print out the whatever's in here. Okay, and so we matched it up. Yep, we matched up with the earliest note in the buffer. Did we? Yeah, we did. That's fine. And we raise an error. Yeah, so the other place we need to raise an error is if we go through the whole deal here, right? And we don't find anything which matches. So what's a good way to do that? Probably we'll do it this way. Note equals none. And then as it goes, if it finds the, if it finds match, it sets note to whatever that note should be. Removes that and breaks. So it jumps out of that inner loop. Okay, and then at the end of the loop, we're just going to check. If note is none, which means we never found a match, then we're going to raise error here. Okay, and we just need one here. Okay, so far so good. Last thing to do is we need to add the note back into our notes. Okay, great. I think that's it. No error messages from MyPy, so that's good. So now that takes a bunch of messages and gives you a list of notes after. Okay, let's test that out. So now when we do the map to 12 tone, we create our message array, and then we need to get our notes. Equals get notes. And that calls, we need an iterable message, which is our message array. Okay. Now we send our notes, well, we have a bunch of these. And to change the pitches, we can set pitch on each note. So what we can do is for note in notes, note.set pitch. And let's give it 99 so I can spot them. Okay, and then the last step is to write out a file, right? Let's just split that out into its own thing. Def write MIDI file from okay. Create MIDI file. Okay, so we have a new MIDI file. We create a new track. We append our track for message in messages. Stick it in the track, return the new file. Cool. Okay, last step here is map to 12 tone, create MIDI file from the message array. Now we can return that. Cool. Okay. Let's try it again. And before we do anything, we're going to try printing the MIDI file before and after. I'll just do it this way. Okay. Let's give it a shot. So I think this error is coming from when I'm trying to save the file. That's why I'm ignoring the error for now. I just want to make sure the other stuff works. So let's see, before, this is our value before, right? We have all our notes, okay. And then after, ooh, looks like the error happened before I got to the after. So line 81. Yup. Line 63 happened in get notes and line 47. This meta message object has no start object. Okay. So the problem is I am going through this end buffer and some of these are not the right message apparently. Okay, so maybe what I do is I'm just gonna print the start buffer and end buffer and make sure I'm getting the right messages in there. I'll just comment these out. Okay. So let's see what kinds of messages I'm getting. So these are the start messages, and I see we're getting some stuff that should not be there, right? So these note on messages are great, but these are not, because these are meta messages. You can see that should not be in there. And if I jump down to these, similar. So yeah, it's definitely doing something screwy here. First of all, it's adding it to both the start and the end buffer, which is definitely not okay. Oh, I see why. Because these are functions, but I'm treating them like not as functions. Oops. I forgot. Okay, so the problem was I was treating these as like booleans, and they are functions. You need to call them with something, which is message. Okay, that should work. Okay, now there's an assertion error, so that means we are getting further. Let's see. Okay, so the start is either the start is too early or the end is too late. Right. Start should be greater or equal than 0. Okay, nice. We're back to the original error. let's see. These should be note on events. So you see all the velocities are 80. Here, all of these have velocity 0, so they are note off events. Excellent. And it looks like they lined up everything correctly. So let's make sure that the after MIDI looks correct. And we will get rid of those other debug print statements. Don't need those anymore. Okay. Hey, progress. So now you see all the notes are 99. That means we changed them successfully. And we just need to actually save out the file now. Okay, so let's figure out how to save. So time to pull up the documentation again. So, and actually I'm just going to sort out my windows here so everything's a little nicer looking. Just going to rerun this with just the error message so you can see that, and also see this. So it says message time must be int. So somewhere I'm getting message time which is not int. Okay, well, let's go check it out. Ooh, you know, I have a hunch. Okay, I have a hunch for why this is happening, because I did notice when we were printing out the whole MIDI file, at times the time was integer, but then at other times it got turned into a float. That is suspicious indeed. It really should stay an integer, and somehow it's not. So let's go find out where that's happening. I'm just gonna print something from the file so I know when it stops being an integer. Okay. Oh, it's not subscriptable. Okay, let's just print the whole thing. Okay, so you see these times are fine, right? These are integers, and then these times are no longer integers. So somewhere along the line, it stopped being an integer. Let's see where that happens. So we know it happens somewhere in map to 12 tone. We're just gonna use print statements to figure out where, because I am lazy like that. Is it here? Yes. So when we call message.copy, it does something to the messages in order to, and turns the times into floats. This might be an issue with MIDI, this framework, actually. I wonder if it is an issue with this library. Let's do a quick search. MIDI objects or Python. We're gonna look at issues and see if it shows up. Float. Why message must be int? Here it is. Yeah, this is exactly what we're running into here, right? So they say the time attribute in a MIDI message, all the messages have a float time, but then when you try to save it out, you have this problem, right? Okay, excellent. Interesting. So it does look like it's probably one of those things where it's a bug with the library itself, right? It's not really a bug so much as it is kind of a not ideal behavior. Really, it should be giving ints, and somewhere along the line, somebody made a bit of a mistake or something. That's my suspicion. So yeah. You know what it is? It might be intentional because we have this ticks per beat, and maybe that's set per track. So when you pull something from a track, you have a consistent value for that, right? But when you have two different tracks, maybe they have different ticks per beat, and then you can't have that number anymore, so it gives you a float instead. So I think the correct way to solve this is to probably... so here's the tricky thing, right? A track is like a separate instrument in MIDI, and you can have multiple tracks going, but the problem is sometimes you also have pieces where, hold that thought. Hello, welcome to the stream. Thanks for joining in. I am currently in the weeds with a brand new Python library for managing MIDI files. And the reason why I'm here is because I am trying to build this program that will turn music into 12-tone music. Basically make it sound worse using math. So the backstory is a little bit about, Schönberg and 12-tone music, which I talked about earlier. But the basic idea is that they did this all manually, where they had to take 12 unique notes and figure out how to arrange them to make interesting music, and then repeat that process for the entire piece. And we're just going to automate the whole thing. And the reason why is because, I was working very recently on this permutations project for neural networks, but unfortunately that got scooped, and turns out a lot of people were working on this thing that I thought was super obscure and didn't matter. And so now I have this knowledge of how to solve permutations and nowhere to use that knowledge except on 12-tone music, apparently. But so basically, skipping all the details, we are going to apply this permutation finding algorithm to 12-tone music, and currently we are at the input music phase. So we're just trying to get the music into the computer, and I'm running into some snags with this particular library to do that. So let's jump back into the library here. So our problem currently is that time exists in two formats in this MIDI library. It exists either as an integer or as a floating point number, so a decimal number. I'm trying to decide whether to do things by track or by file, because the way this works in MIDI is that the music is split up into tracks. So you have one file and then multiple tracks, and each track is like an instrument. It could be the same instrument, it could be different instruments, right? But they act as independent instruments. So that means they have their own timeline. And so, like, for example, instrument track 1 might have a note at time 1, and its timestamp will be 1, but track 2 could also have a note at time 1, and its timestamp will also be 1, right? Because they maintain separate timelines as they go through the piece. The problem is I need to be able to collect all the notes in one place in order to do this 12-tone thing. I need to collect groups of 12 notes, and they need to be contiguous in time. I can't have separate lines. Well, I could choose to split it up by track, but I'd like the option not to. So basically I need to make a decision now. Am I going to split things up by track, or am I going to combine it all into one? And my decision is to not make a decision. I'm just going to do it with a flag that lets me pick and choose which way I do it. That's my decision now. So here's the idea. When we run the part where we get the notes, I think, here. When we run the map to 12-tone, the first thing we do is copy all the messages into an array. And what we need to do here is make a decision on whether we are calling this for everything in the MIDI file or whether we're going to do things by track, right? So maybe we should pull this out of here and put it in the very high level here at the very beginning. So after we open the MIDI file, we're going to have a choice. If we'll call this, we'll create a temporary flag like by track, combine tracks, let's say. And we'll say false for now. If combine tracks, if we want the tracks to be all in one, then we are going to do this. But we also need to change the timestamps to a consistent one. So the easiest way to do that is probably, for now, I'm just going to take... We need to go through the tracks, figure out what the time tick is, like how fast the tick is. So in MIDI, let's see, what does the documentation say? Documentation says the tempo is given as microseconds per beat, okay? And when they convert, they take the integer, which is the time step of the note messages, divides by ticks per beat. Okay. So the problem is we still need an integer, which means that when we convert back from this float, we need to get it to some common amount of ticks per beat, right? So let's see, to convert back from float to integer, we need to multiply by ticks per beat. And I'm just going to fudge it a bit. I'm going to pick some reasonable ticks per beat, like the first channels, the first tracks ticks per beat, and then convert by multiplying. And then if I still don't get an integer, I'm just going to round to the nearest one. So it's a bit of a fudge. It won't be exact, but it'll be close enough. Okay, let's do that. Now I just need the ticks per beat for a track. So let's go back to the docs for Mido, this library. And what we need is tracks. So I'm just gonna open up a separate window to search for track. File types, yada, yada, yada. Is there a way to like look for tracks here? Ah, yes. So when you open a file, there's a list of tracks. I see. And each track has messages. Okay, cool. So a little later, I'm just gonna skip ahead a bit first to figure out where we're going with all this. What we want to do is once we have the tracks, or one track, which contains the notes we care about mapping using the 12-tone thing, we're going to go through all of these tracks and run map to 12-tone. And so now we need to change this a bit because we are no longer doing it this way. We're doing it this way. And this is now going to be a track. And we'll call this a new track. Okay, cool. Of course, we still need this, but we're going to move it down here. So I'm just reordering the logic a bit so that we're going to handle things within a single track in the map to 12-tone part. And outside of that, we are going to decide whether all the notes should live in one track or if they should live in separate tracks, and kind of call map to 12-tone differently depending on what decision we make. So here, we are no longer bringing in a track, actually, it's just a bunch of messages. Okay, great. That's good. That is... Let's see. I should probably copy these messages, just in case. Just in case. Because I don't want to be changing things that I don't expect should be changed. So I bring in an array of some kind. I copy out all those messages. I get the notes within those messages. I do something to the notes. I create a new track. I put all the messages back into that new track. I give you back the new track. Okay, and then out here, I need to create this array, right? So there are two things that can happen. If you want to combine all the tracks, then you need to create this and also edit the timestamp, convert from float to int, okay, and then call, and then you're good. Else, if you're not combining them, then you just give the tracks out, right? So now for track in tracks, here, we're gonna do it this way. So I'm working a little ahead just to kind of get an idea of how this should work. Track. So I'm gonna create a new MIDI file here. I need to add the tracks as I create them, and then save it out. Okay, that's good. So we're missing this part, right? The missing link is this kind of array or list of messages per track. So in this list, basically, it tells you which things you should call map to 12 tone on independently. Right? So here, we need to create this as a list of lists. Now, so it's a list of tracks, each of which is a list of these messages. And if we want to combine the tracks, this is fine. We just need to do the conversion after. If we don't want to combine the tracks, then we need to go through every track. MIDI.tracks. I'm just looking here now at their documentation. So you called this, and then looks like, yeah, so I think that's fine. I'm gonna create it all the way back here. This is our container of tracks. Oops. Let's separate it out a bit. And we'll stick this in. And we're just missing the conversion step, so we'll skip that for now. Instead, messages per track, we are going to, so this part, we just stick all the messages into one track and stick that into our container. Here, we need to go through every track and add that to our container. But first, we need to convert this into messages. Something like that. Okay. Okay, so that should do it. Okay, for now, let's turn combine tracks off, which it is, so we can skip coding in this time converting function and just try running it. So let me shift some windows around. Clean this up. Okay, well, nothing happened because I didn't ask it to print anything, but at least there's no error, which means it's saving the correct thing out now. Let me just print out this file before I look at it elsewhere. It looks good. So let's open it up as an actual sound file now. Exciting times. Where is it? Test scale, right? We're in the out directory, test scale. Okay, you hear that? That is the sound of success because we've turned every note into this 99 pitch, which is some note that's higher than the ones there that were there before. Just for reference, this is what it sounded like before. If it wants to play. Oh, you know what? I will play it from here. This is the original. And this is our messed up one. Okay, so we've made a step forward. We can actually manipulate the notes in the file now and output whatever we want. That's great. So we're finally past that part. Now, of course, we're just missing this conversion, right? And I'm just going to leave it for now. Classic programming, we just leave the to-do statement in there and ignore it and move on. Next problem. Let's see, it's 10:40, so I'd like to get just a little bit further. Let's skip the... So originally I said we need to do a couple things. We need to input some music, which we did. Yay. We need to split up the music into 12-note chunks. And that sounds kind of not fun. So let's skip that and jump straight to here. We're going to do this next. We're going to actually do the 12-tone thing. So that means we can only work on 12 notes out at a time. And so for now, I'm just going to pick the first 12 notes in the music. And we're going to do the 12-tone transformation on the first 12 notes only, and then worry about everything else later. Just so that I can, hear some progress today. Progress is important for morale, and morale is important for actually getting things done. So music on, let's give it a shot. Yeah, okay, big stretch. Pet the cat. They're gathering for dinner, it's that time. Okay, hydrated, let's get into it. So right now, map to 12 tone is just taking all the notes and setting them to one pitch. That's kind of our dummy operation. We need to do something serious here now. So, what's the plan? We need to create a group of 12 notes, right? So for now, we're just gonna create a dummy function to do that. Call it split into 12 dozens. Call it split dozens. Save some typing, right? So this takes the notes in, the array of notes, and gives you groups of 12. We're gonna do something. Okay, so we can get rid of that. And we need a new function that does the split. And we're just gonna, as I said, I'm not actually filling out this function today. We're just gonna fake it. Actually, you know what? It's not that hard because we're just gonna go through notes and just yield every 12 of them. What's the easiest way to do that? I'm gonna do it the dumb way because I don't want us to think about it too hard, right? So for note in notes, there is definitely a Pythonic way to do this. Like there's some fancy iterator. I'm just gonna search it up. Python group array into chunks. Stack Overflow is always the way to go. Don't trust any other site. The other sites have way more ads. That's why I always go to Stack Overflow. Ah, okay, yeah, I forgot about this. You can do array indexing, so we're gonna do it this way. I in range, so we're just going from 0 to the length of our thing, notes, and we go by dozens. We'll actually make this a little more generic. We'll call this split into groups. And that way we can also give it a argument in case we want to do something else later, and which we might. Like, just because we're doing 12-tone music now doesn't mean you couldn't do pentatonic scales later, right? So we can change the number we split by, split size, okay? And so now we can specify whatever we want. In this case, we're doing 12. Okay. And then, let's see. So basically for each of these, we go, right, notes, and we can do smart indexing using Python, which is from I to I plus size. Yeah, okay. And the last thing to do is just wrap that all. You know what? This is getting to be a bit of a long line, so I'm just gonna split it up. I mean, it takes more lines of code, but I think it's a little neater. Groups equals that, groups.append that, and then return groups. Okay, that was easy. Now, there are probably more sophisticated ways to do this split later, especially when we have notes that overlap in chords. So that's why this is a bit of a placeholder, right? We'll say to do chords. For now, though, it's going to be first come, first served in the 12-tone gravy train. So we have group, split, groups, okay, and then for each group we're going to do something to it, which is the actual map, right? So remember what we were doing here. We need a loss function. So the way this works is we first need to decide how good a pairing is. So we're going to have on one hand the original notes, and then on the other hand we have the notes that are getting that are from the 12-tone permutation. And so for any pair of original note and 12-tone permutation note, we need to calculate how similar they are. And for now, we're just going to go with the simplest solution, which is just straight up how far apart are they thing, right? So, so I'm thinking a few steps ahead. We also have the issue where we have notes that are unique on the keyboard, but actually what we need is notes as letter names, right? So that a C that's low is the same as a C that's high. We don't care which C it is on the piano. We only care that it is a C. So we need to convert our MIDI note numbers, our pitch numbers, into those letters. So we need some function to do that. We'll call this MIDI pitch to convert MIDI pitch. Int MIDI pitch, and it gives us an int. Oh, I've been forgetting to do that, right? I should probably include these function annotations. Split into groups will give you an iterator, an iterable of iterables of notes, and then here we have an iterable of notes coming in, and size is an integer. Okay, lovely. Oh, that is backwards. MIDI pitch is an integer. Okay, great. We got that. That's good. Okay, so we know that 60 is middle C, right? So let's just go from there. We'll subtract 60 from the MIDI pitch. So now 0 is middle C. And then everything should be modulo 12. So we just need to divide by 12, and the remainder is going to be our pitch. Yeah. Now I'm thinking ahead again, and I just remembered that we could split into groups in an arbitrary way. So do we need that functionality here? Probably not, but maybe we'll need a way to convert between different scales later. So maybe I shouldn't do it this way. I'm gonna rename this a bit. Just to make it clear, this isn't just any pitch. These are chromatic pitches, so it's like all 12 notes on the keyboard. That's what it converts to. And if we need a specific scale later, we can convert from that to the scale. Okay, so we'll just have a two-step process. Pitch equals chromatic pitch equals MIDI pitch minus 60. And then we're going to modulo that by 12. So we divide by 12, take the remainder, and that way it loops over itself every 12 notes. And that's all we need to do. So we just need to return this. Let's just return it straight up. Who needs more code? 60 is middle C. As a reminder to myself. Okay, so that should work. Now back to the grouping. So in every group here, we need to convert all the pitches first. MIDI to chromatic for the pitches. Pitch for pitch. Oops. So what I'm doing here is I'm going to take every single pitch in this group of 12 notes and turn it into a chromatic pitch instead of the original MIDI pitches. Okay, and then we're going to run the actual 12-tone algorithm on that group. So here's where the loss function comes in, right? You can think of it this way. We are trying to match up the notes in group with the notes in 0 to 11. Let's change that into a set notation. Okay, so that's our goal here. Right? And so the first step is we need a loss. We need to calculate losses using a loss function for all pairs between these two, right? Between the notes in the group. Let's call that source. Maybe that'll be easier to follow, I think. Yeah. Okay, and then we need to match that up with target. Target is just all the numbers from 0 to 11. So here we're let's start using NumPy. NumPy is the numerical library for Python, and it's gonna be relevant because it's a lot easier to do the loss calculations with NumPy. So let's install NumPy. Pip install NumPy. And it's cached because I have NumPy on like every project. Yeah, it's really useful. So anyway, now that we've installed NumPy, we can import it. So we have import NumPy as np. And then if we go back, we have target equals np dot arange, which just gives us a range of numbers. And we want 0 to 12 exclusive. So we don't even need the 0 here. But we also want the data type if I can change the data type directly here, yes, I can. I don't want it as integers. I want it as float because that's the way you're going to be able to calculate loss later. Now, loss is basically a floating point operation. You can have any amount of loss from, 0.0001 to like a million, right? So it makes more sense to think of loss as a continuous value, right? It can change, even though we have discrete notes, we want to have the flexibility of a continuous loss function. So yeah, let's make those floats. In fact, the source should also be floats. So I wonder if I should do that here. And let's, while we're at it, let's go into NumPy land earlier. So we're going to convert the source into a NumPy array already. And the data type is float. Actually, no, I don't want the data type to be float yet. I'm going to do that in MIDI to chromatic, I think. Does that make sense? No, it doesn't. Okay, let's just do it after. So source equals nmp.array, and the data type is float. Okay, nice. Okay, so first we convert the pitches, then we create our source and target arrays, and then we calculate our losses. So for the losses, we need every single pair here, right? So we are going to fill an array that looks like this. The source length is 12, right? And the target length is also 12, so that's the same. And then because we are matching 12 things to 12 things, the total number of things is going to be 12 squared, right? So we need a matrix of 12 by 12 size to store every single pair of losses. So I'm going to pre-fill this because that's a little more efficient. It's also easier to index that way. So we're going to have np.non, probably, no, full. Yeah. So yeah, you're right. Let's just fill it with zeros. Who cares what it is? Or actually empty. Empty is even better. So empty gives you a new array, but doesn't put anything in it. So it's whatever is randomly in memory at the time. So empty. We need a shape. The shape is n by n, n, and the data type is float. I think the data type's always float by default for this, but I will make it explicit. In fact, let's put the n here, right at the top, and stick that anytime we have 12. Just so it's a little more flexible later if we need to change it. Okay, and we'll call this losses. Now, for every source and target, we are going to compute a loss. And to do that, we need all the indexes from 0 to 11, like 12 exclusive, right? 0 to 11. And then we need a separate index, which also goes from 0 to 11 for each of those. So it's 2 nested loops, or you can use, I believe, product. So that's a handy Python thing, which is equivalent to running 2 nested arrays. And we have range n twice. And this just takes what we call the direct product between these two things in math. The direct product in layman's terms is take every possible value from the first thing and match it up with every possible value in the second thing. So we end up with n by n things, and now we can index the right things to create our loss. So we need some kind of loss function, which will operate on our source note at I, and our target note at j, and then we're going to take the whole thing and stick it into losses at ij, like that. Okay, great. So you can see we're missing this loss function part. Let's not pick a specific loss function for now, and we will just call it a callable. So it's an argument. We can pass whatever loss function we want into here. And the only stipulation is it operates on these chromatic note values. So the notes are from 0 to 11, 0 to 12 exclusive. Okay, so once we have the losses, we do the magic after that, which is the finding the permutation part. And that is very easy because we're just going to use someone else's code. Specifically, we're going to use SciPy. And let me just search up the correct thing. SciPy linear sum assignment. And I'm very familiar with this because I just used it for that neural network project. So yeah, it is this SciPy optimized linear sum assignment. So we need to install SciPy, which is the scientific Python library. Pip install SciPy. And again, it's cached because I've been using it recently, apparently. Okay. And then we can import SciPy. From scipy.optimize, import linear sum assignment. Okay. And last step is to actually use it. Map to 12 tone. So we've got our losses here. After we have our losses, we just have to run linear sum assignment. Now, what does this magic function do? Well, let's read the docs. The documentation say, if I close up some details here, it says SciPy linear sum assignment solves the linear sum assignment problem. Well, that's real helpful, buddy. So what the linear sum assignment problem is okay, it's also known as minimum weight matching. And the idea is that you have a bunch of things. You can kind of ignore this language. Basically, you have a bunch of objects. We'll call them vertices here, but there are a bunch of objects, and you need to match, something from group A to something from group B. But you can only do that once, right? It's that whole thing about this function needs to be invertible. It needs to be a one-to-one matching. Any one thing on the first set needs to have one partner in the second set. It's like dancing, right? You have one partner. You can't go off with three partners. I guess that's not socially acceptable. So that's the basic idea here. And this function just solves that problem where you pick the assignments so that you minimize some kind of cost. And that cost is, of course, the losses we just calculated, right? So the losses are for any pair, but then now we're assigning pairs so that we minimize the loss overall while still maintaining that one pair per object kind of requirement, which is basically the exact same thing as making a permutation that satisfies the thing we want, right? Which is the whole point of this project. Okay, so what does this take? Let's see. The parameters are cost matrix and maximize. So I need this. I need the docs again here. The documentation says I need a cost matrix, which is our losses, and our maximize, if we want to maximize, which we do not. We're going to assume loss means bad things. So the bigger this number is, the worse it gets. So we do not need to maximize. So by default, that's false, which means minimize, and it's going to return row and column indices. So that's the permutation we want, right? So basically, this is a list of here's the things in order which you need to minimize this cost, and similarly with the columns. So, okay, that was easy. Isn't it great to steal code from somebody else? So what do we do with these indices? Well, we just need to sort our things. Actually, it's a little more complicated than that, I forgot. Which is we need to sort our source specifically. We need to permute the we need to permute the target, because the source is our input music. We don't want to change that, right? That's the thing we're going towards. So actually, it really should be called target. Wow, why did I call it source? We'll call this the real music or something, because this is the real the notes we want this music to sound like. So our real, we'll just call it real music. And we'll call the target the 12th tone. We'll call this the row tone. Yeah. Okay. This is kind of more Schönberg's terminology. The tone row is the row of 12 tones that you get to use at any given time. So some future, like I'm thinking ahead, right? Some future improvements to this algorithm would be something like reusing the same tone row as much as possible, or like, you know, being able to flip it, like transpose, invert, or otherwise like transform this tone row by keeping it otherwise the same. And the reason why this is important is because that's how Schönberg wrote his music, like, or Albenberg or Anton Weber. They really tried to use the same tone row over and over. And it's very common in music, right? You have some motifs, you want to repeat those, and through repetition, you get a piece of music that sounds more coherent and designed, right? Something that's more meaningful than random notes. So that there's a lot of places like that where we can improve the musical artistic quality of this algorithm, which is kind of more subjective, right? It's about choices that influence the loss functions we choose, and then the loss function influences what the computer decides is the best assignment. Okay, so I'm getting some kind of weird bug here. Oh. Okay, apparently I'm getting something that's the wrong object here. Okay, I see why. This is a list of notes, right? And we want the pitch. Okay, so let's change that. So in our note object, we do need a way to get the pitch. And we will just make this a property of this. So what that means is you don't need the brackets to get the pitch if you wrap it in this decorator property. The actual pitch comes from our source. We'll just use the start to refer to a pitch, and the place you get it is this property called note inside this message, and we'll just return that. Okay, cool. So going back to here, we have note.pitch, MIDI to chromatic, and oh, I should set my so I also need to tell the linter, the MyPy that's checking my code, to give me the right thing back, I think. That is an iterable. That's not good. Okay, so small changes. We're going to change this to a list. That should work. Yes. Okay, that works. So little things. The type checker is complaining because I have an iterable here. Iterable does not define some things like length or indexing. And so now that I've changed it to a list, lists are indexable and they have lengths, so that's all good. Okay, so while I'm here, let's take a look here. We have a similar issue here. Messages is an iterable. Let's change that to a list. Yeah, so these type things generally don't cause issues in runtime because these things are lists, so they do have lengths, but the type checker doesn't like it because it thinks that we didn't think about that. Easy enough to change. Okay, and last step here. How's that? Will you stop complaining? One of these is returning something that is not what I want, I think. Split into groups. Is it giving me a list? Yeah, it is. It's fine. Stop complaining. Oh, list int, expected list note. Okay, that is important, I think. Split into groups. Right, okay, this is the wrong place, that's why. Okay, so the type checker actually helped me there, I think. Wait, no, it didn't. Yeah, that's fine. Yeah, because note.pitch is a int, so yeah, stop complaining. Okay, moving on. Okay, so where were we? We need to... Okay, we have these indices, and we need to match up our tone row to the real notes. So, we need to permute the tone row according to these indices that the linear sum assignment gives us. So, I think we can just apply NumPy's indexing directly to this. So this gives us some ordering, and we're just going to stick that straight onto tone row, I think, because row index is usually... I'm pretty sure row index is usually just the numbers in order, so it doesn't permute the rows. I'm just gonna check that. Arrange n. Okay. So if that's the case, all we need to do is rearrange the tone row according to the column indices, and then we're done. That's our 12 tone. Let's just call it permuted notes. Okay. So once you've done all of that, permute notes, and then we need to save them into something, right? So what's the best way to do that? Well, the problem is we still have this messages array, and we need to be editing that. So actually what we should do is just iterate through the notes we have, these real notes. For note in real notes, we are going to... Hopefully I haven't used this anywhere. Nope. Okay, so for each note, we are just going to replace it with the permuted pitch. Okay, I'm just going to change it up a bit. Okay, so what we're doing here is we are going to collect every note in this set of 12 with the pitch that we calculated, which is optimal for it, in this 12-tone tone row. And then once we have the correct pitch and the correct notes in pairs, we just set each note's pitch. Like that. I think that's the right thing, right? Set pitch. Yeah, that's what I called it. Excellent. Okay. So note.setPitch, note.setPitch. Okay, so once you do that, all the notes automatically calculate, like they save out the right message to get this new pitch, and then we save out into a new track. All of the notes were done. That's it. Okay, we are missing one thing, which is this loss function. So let's create a real easy loss function. We will just do that L2 norm loss function, which is like Euclidean distance, also known as like squared error, and something like that. So the way it works is super simple. We'll call this loss, L2 loss. We have pitch. We'll just say XY. We don't really care what they are. And let's see, we have so X and Y are numbers. We are going to have x minus y, and then we're going to square it. That's it. Really easy, right? It's whatever difference you have between these squared. So the reason why you square it is you can't have it be negative, right? If your loss is negative, that means it's good, right? And that doesn't make sense. We want the distance to be bad. The further away, the worse it gets. And that's what the squaring does. In fact, the further away, the worse it gets. Like it gets even more worse when you're further because of this squaring thing. So now that we've got that, wherever we call map to 12 tone, we need to include the loss function, which is L2 loss. And that should be it. That should be it. So let's give it a try again with the test scale. We will run it and probably run into a billion errors. So let's go do that. Python Schönberger. So yeah, immediately you have an issue of set pitch. Right, so this is not... okay, so it's because I originally had real notes be this, but that's not what it is anymore. So we need to rename this to group something different. We need to keep this because this is a group of 12 note objects, and we need that down here. Okay, that should work, right? So now real notes here, that's just the pitches. So maybe we should call that real pitch. Then the tone row is here. Okay. Next error, debugging by fire here. 29 set pitch. I'm not giving it an integer. Okay, that's easy enough. So down here, this was a float because because tone row was a bunch of floats, right? I wanted floats because I wanted NumPy to work in floats. But now that we have the pitches, we just want to convert back to integers. So how do I do that? Oh, this is a single number, so that's fine. I can just do this. Individually. Okay, we're making progress. The next error here, I'll run it again, is line 93. Line 93. Sip and think. Index 4 out of bounds. So something's a little too far, huh? That's a little strange because these should all be 12, right? N is 12. So it's a 12 by 12 matrix in the losses. And I have, this should be 12 notes. And this should be 12. Oh, I see what's happening. So at some point it runs out of notes here, right? And when it runs out of notes, yeah, so when it runs out of notes, what should we do? Because there's some options. We could transform what's left, or we can just give up and ignore them. I'm gonna go with the giving up approach because I just want to finish it now. So we'll say deal with incomplete group at end. And for now, we're just going to trim off the last group. So if the length of real pitch is less than n, we are just going to exit. Just leave it alone. Just bail. So to do that, well, should we even insert them back into the track, or should we just erase them? Just like eat them out of existence. I'm just gonna erase them. So it's a temporary hack, but it will be fine. So we break, I think. Yeah, I think we break. So what that does is it just exits us out of the loop if we're out of notes. Okay, great. So looks like something happened. Sure did. Oh, but those are definitely the wrong notes. So I've got 0 as a note, and that's like, that's definitely nowhere near middle C. It's because I forgot to change these pitches back. So we need to kind of turn them back into the chromatic pitches. How are we going to do that? Okay. I think I've got it. Do I? So the problem is we originally had different octaves for these notes. Then we got rid of that information. Hi. Oh, hello, kitty. Are you concerned about my code? Yeah, she is. Do you want to say something about the quality of my programming? Okay, so like I was saying, we had octave information, and then we got rid of it in order to do the 12-tone mapping, and now we need to put it back. So again, that's a bit thorny, because if we use other loss functions, it might not be that obvious how we're going to do this mapping. So for now, I'm going to do something dumb again, and that is I'm just going to set it to the closest octave that it was in originally. So to do that, we're going to take the real pitch and subtract the permuted pitch. So let's see. Real pitch minus tone row. So that gives us the difference. Instead of the exact pitch, it just gives us how many semitones, up or down, we've moved them in order to get this permuted pitch. And one more thing we need to do is we need to modulo this by 12. And so the reason why we need the modulo is because, well, the problem is we need the smallest possible difference, right? So if the real pitch is like 11 and our tone row gives us 0, the distance there is, the closest distance is -1 in modulo space. So I just realized there is an issue with the L2 loss right now, which is it doesn't take that into account, that the closest distance could be going the other way. So there's a very easy way to do this, solve this, which is we're going to take the minimum between x minus y squared and y minus x squared, I think. Hang on. Almost. So we'll call this modulo L2 loss, because now we're not working with normal integers. We are working with integers that are clock numbers, right? So when you get to 12, it rolls back to 0, and we need to account for that. And so we know everything's from 0 to 11, okay? And the difference is going to be, like, let's say I have 0 and 11, right? If you go one way around the clock, if you go clockwise, that's 11 steps. But if you go counterclockwise, that's only 1 step. So we need to just go both ways. We need to go clockwise and counterclockwise around the clock. And whichever is the smaller number is going to be our loss. So how do we do that? Going clockwise is, let's say y is the bigger one, right? Then you're going to take y minus x. Going counterclockwise, so going clockwise, y at 11 minus x at 0. Going counterclockwise, you're going to have x at 12 minus y. Okay. So we do need the modulo number. So I mean, so much for the float, right? Maybe we don't need the float, but that's okay. You can still return modulos this way. So let's see. So we'll say a big A. Let's make A the bigger one. A equals max xy, and then B equals min. There's probably a more efficient way to do this, but I know this way is correct, right? So we will stick with that. And then we are going to return the smallest of either A is the bigger one. So let's actually switch that around because it seems more intuitive that way. Oops. Okay. A is the min, B is the max. Now we're going to do B minus A for one direction, right? Does that work? Does that work? Should work. Because B minus A is always going to be positive. Because it's going, yeah, okay. And then on the other hand, we have A minus B, but A is going to be a little higher up. It's going to be one full rotation around the clock. So that way, when A minus B happens, it's also positive. Okay. Great. Now let's actually separate out this modulo logic into its own thing because we're going to need it again when we do this part, the set pitch part. Hello, cat. I can't see my screen. Would you like to move? Okay, cat removal service before she starts typing, and she's done that before. This one likes to type on my keyboard. Yeah, and she's quite dangerous if you have any kind of editor out. So we are going to remove you from the premises. All right, back to this. We are almost done. Half an hour left, so I think I can finish this for tonight. Let's see. So we want the smallest distance in modulo land. And so to do that, we're going to create a new function called smallest mod distance, or just mod distance. X. And we're basically copying this whole thing. In fact, let's just copy the whole thing over. And the only difference is we're not going to square anything. We're just going to return the distance, but also not. Oh, right. So what we want is a signed distance, so we know whether it goes up or down. It's really a mod diff. But we also want the smallest such difference. So to do that, need to change things a bit. So clockwise equals B minus A. Counterclockwise equals this A plus mod minus B. And then if clockwise is less than, so if the absolute value of one is less than the other, you're going to return that one. Otherwise, you return the other one. Okay. There. Okay. So now the only thing we need to do in mod L2 loss is do that difference. Mod diff xy mod. And we're going to just square it. That's it. Okay. Great. So now we need to change a few things. We need to call mod L2 loss in the loss function. And we also need to pull this mod diff down here. So we are going to take the mod diff between real pitch and tone row. So let's do that. Mod diff yx for hang on, just checking something, make sure I'm doing the subtraction correctly, because I also need to make sure that the difference is going in the right direction. That's a problem here. I forgot about that. So we're going to do y minus x. Just as a convention. No, we'll return x minus y, because that's a little more obvious. So we just need to change something here. If x less than y. If, let's see, x minus y. So if x is bigger than y, it's going to be positive, and this always returns positive, right? Now, that means okay, so we just need the sign. Okay, so I'm just going to change it how I calculate this a bit. This gives us the sign of our answer. Clockwise and counterclockwise give us our magnitude. So we just need to return whichever one is biggest. Or sorry, smallest, not biggest. We don't want the biggest one. That's the whole point of this. So the smallest one, but times the sign. There. Okay. So back to here, we have mod diff xy, and we're going to do this for every xy in zip, the real pitches and the tone row pitches. And I'm just gonna do this: permuted equals tone row, and then run permuted here, diff from real. So this. Diff. So now we can do this. We can change the pitch according to the original pitch, which is note.pitch, and then we're going to add the pitch difference onto there, like this. There. Invalid syntax, though. I'm missing. Okay. That should be that. Oh, I need a mod. Okay. Alright, let's go back to it. Oh, I'm still missing an argument. 104. The losses need an end too. Okay. Okay, that looks more promising, right? So now we have 60 as our start and 60 as our end. Let's see. It should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the first 12 notes, and they should form one group. So let's see if that's true. So we're looking for repeats, right? We should not have repeats. It should be like 0, 1. So we've got 0, 1, 4, 5, 7, 9, and 12. That's 12. That 12? That's a little weird. Okay, 11, 10, 11 again. Okay, so something's wrong here for sure, because we should not be seeing 11 twice here. Huh. That's interesting. Okay, so looks like we have to do some debugging. I'm just gonna print out the group here. And there should be only one group here, I think. Yeah. So I'm printing a bunch of notes, but let's actually print out the pitches. And to do that, I'm going to go to the notes object and just give it a little quality of life here, which is to give it a string representation. So we will return a string with the pitch. Yeah, okay. We'll just start with that. Like that. Okay, let's try that. Okay, so that's our first group. 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, that is way too many notes in that group. What happened? We group in groups. Oh, it might be printing two groups here. Yeah, okay, it's printing two groups, that's why. So the first group is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. How about after? After I set the pitches? I really should do it again. Okay, so let's see what happened. So 62 became 1, okay. 64, no change. 5, no change. 7, no change. 9, no change. Okay, 2 became 1. 1 became 2. What? Why would it switch those around? That's a little strange. 0. Okay, this is where it goes haywire. Right here. So, let's see. We have 0, 1, but we're missing 3. Nine 72. My guess is that this pitch difference is screwing it up. That's my guess. So let's take a look at permuted first. And we'll also look at the original pitches. Okay. So the original pitches are these. Here's the permuted ones. Are there any repeats here? No, there are not. So this part's fine, right? It's when you convert it back into the differences from the real pitches, that's where things get screwy. So let's see what's happening there. Okay, so we need the differences. Let's take a look at those. Way back up. Okay, so we have original pitches, the new pitches, the 12-tone pitches, and then we have how much we need to change the original ones by to get the new ones. And keep in mind, this is a scale, so it keeps going up. Let's see. So, I mean, it looks pretty good, right? This is 0. This is -1. These are 0. Okay, we care about this part. So what happens here? Okay, this. Okay, here, 11 goes to 10. And the difference, let's see. Here, it's going up 1. And I think it's just going in the wrong direction, right? This should be down 1. So I think I just got the sign wrong somehow. If x is less than y, it should be 1, and if x is... that's kind of weird. Why would that be wrong? I think it's actually the issue here. When I calculate the difference here, It should be Y and then X, because this is the real one, right? The real one, and then the permuted one. Okay, I see. Okay, I think that's better. So now you have +1 to get 2 to 3. And then 11 to 10 should be -1, which it is. 0 to 1 is +1, good. 0 to 2 is +2. And then the last two are -1s. Okay, perfect. Let's generate and take a look at what that is. So now we're going to just print the new MIDI file here to check. Okay, the first 12 notes, 60, 63, 64, 65, 67. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hey, look, they're all distinct notes now. So it should sound kind of screwy. And let's go see if that's the case. So I'm going to open up that file. This is exciting, you know, when something actually works and you didn't have too many bugs, it's always a good kind of moment. So let's hear it. So I'm gonna turn this off. Okay. I mean, you can already hear it sounds pretty darn screwy. So just for comparison, here's the original. Nice, pretty scale. Right? Nothing special there. And here's our awful 12-tone version. Yeah, I'd say mission accomplished. We did it. So since we're here, of course, we shouldn't finish without trying some bigger pieces. So I've got a couple here. I've got a couple silly little pieces here. What do I have? Let's see. I have the Well-Tempered Clavier by Bach, Prelude 1. It's quite quiet, so let's see how that goes. Oh wow, that's really quiet. Okay, I need to turn this up. Okay, let's turn this into some abomination. So, going into our Schönberger zone, we have this, right, we have it already. It's right here. So we just need to stick it in here. So we will say file equals this. And we'll just replace each of these. Okay, so now it saves, it loads from MIDI and saves to out whatever file we put in here. Let's give it a shot. Oh no, there's a missing note. Note on channel 0. So it's not able to find an end note, which is, okay, that's annoying. Before I debug, I'm not going to debug this tonight, so let's just try a different piece. Let's try the Turkish March. I've always wanted to do this. So this is the piece by Mozart. It's not really called Turkish March. It's just the you know, the metronome marking for this piece says Alla Turca, so it's now known as the Turkish March. It was written in Vienna when they were under siege by the Ottomans, hence, you know, the Turks, right? The Ottoman Empire from Turkey. So yeah, it has a lot of that kind of Turkish influence in the, I think it's the percussion of that piece. So let's turn it into the Schönberg March. How do I do that? Here. Do I have it? Oh, I already copied it over. Look at that. Okay, let's try this. If this doesn't work, I think I will have to debug, because I really do want to hear this one. Yeah, so again, it says there's an orphan note. That's unfortunate. So there are some notes in these pieces where something is happening, and it's not able to find how to match up the starts of the notes with the ends. So let's print an extra message here. Let's print out everything in start. Okay, that's a lot. Wow. Okay. So there's nothing in end buffer. And we are at note 13 here. You know, one way to do this is just ignore them. And this sounds horrible, but maybe we should try that. That is interesting. So I don't know enough about the MIDI standard to say whether you're allowed to have notes that just start and there's no end. But we could just try. Like ignoring these. So yeah, we're just doing the classic. It's not a bug, it's a feature now. Okay, so instead of raising an error, we're just going to let you know there are some issues and then continue on as if nothing happened. Yeah, so there's quite a few notes where you can see that, yeah, you can see that they are missing endings for some reason. Okay, that's fine. Let's just see how it goes. So, before I play this and blast out your speakers, let's hear it first. Okay, not the prettiest version, especially in that part. That's definitely not how it's supposed to go. Now, keep in mind, the original was for orchestra, classical era orchestra, so not the modern orchestra, the small orchestra. But this is kind of for, this is like a demented version for piano. Now we're just going to see how much worse it gets. Actually, we are not, because there's an error here. There's a none type object. Huh. How did that happen? So there is a note in here, which is none. What? Well, there's an easy way to find that. Just print until you get it. Oh dear. So you have a whole bunch of nuns. How did that happen? That is certainly a problem. Everything is none. Okay. So something is wrong with these notes, is what I'm seeing. Okay. So when it's getting the notes, we need to know what's going on with these notes. Okay, so there's a whole bunch of notes. There are note on, channel 0, note 74, velocity 92. Okay, those are notes. Those are definitely notes. I'm just printing out something slightly different. What a mysterious problem. I wonder if all of these notes just have starts but not ends. I really do wonder. You can see it creates a note here. So I guess we are going to figure out what exactly is being created here. I'm not seeing it. Is it even creating any notes? That's the question. Okay, I'm gonna print it out after all the warning messages so that I can actually see what's going on. And I'm going to print out you know what? Let's do something a little more sophisticated, which is right now I have notes printing out just the pitch, but I am instead going to return this. So I'm just going to return the entire message. Let's hope that works. Still giving me a lot of nuns, huh? More nuns than a convent. Let's see. So this thing is none. Oh, I see. We don't want to append it if it's not. That's why. Okay. So you end up with nothing because it didn't generate any, right? Because everything was a none here. So that's kind of sad and unfortunate. So maybe we need to make it so that even if it doesn't find anything, you still create a note. It's just the end message will be kind of not applicable. Maybe that's the way to do it. Okay, so to do that, we just need to change the note object. So instead of requiring this end number, it can be optional. So if end is not none, we need to make this assertion. But if it is none, we don't care. And this is fine, but when we use self.end at some point, like set pitch, we need to just check if self.end is set. If it's not none, then you can change the pitch. Otherwise, don't touch it. Right? And that's really it, I think. Yeah, okay. Excellent. So now, if we go back down to where we were getting the notes, here, if the note's none, which means we didn't get a single one. We did not find a match for it. Instead of doing nothing, we are going to still create a new note, but it's going to have none for the end. That's it. So you still have a start message, just no end message. Okay, so let's see if that changed things. There's our new one. Okay, now just as a reminder, this is what the Turkish march sounds like normally. I remember there was a kid in elementary that played, actually one of my friends at that time, who played this piece around maybe grade 5 or 4, I forget. Anyway, they played a piano arrangement, and it sounded really impressive at the time. Okay, so that's what it sounds like normally. Now here's the 12-tone version. Oh, that's funny. Now, all the notes are being held because there's no end events in the MIDI file. So it's just, everything's being held forever. But you definitely hear, it still sounds like Turkish March. It's just like, it's like the Haunted House version now. This is great. I don't know, maybe it's not great. You know, great is subjective, and I understand that this might be pulling teeth to some people, but I think it's hilarious, and great success. It's like, you know, when the disturbed child goes up to play his recital or her recital. Okay, let's try one more. Since this is so much fun, I'm going to see what else I have downloaded. I have, okay, the WTC, that's the Bach Prelude. This is a very famous piece, also for piano. I don't have too much non-piano stuff here, but we'll try it. Okay. Same problem. There's a lot of orphan notes, and I don't know why. I'm gonna need to dig more into the MIDI specification next time. Okay, and here's, we'll do a before and after again. So here's the original. Although normally you would not play the staccato, like all short notes. It would be nice and flowy. I like teaching this piece. It's actually really interesting from a theory standpoint as well as from a playing standpoint. Okay, let's pause there. And now, evil mode. You know, it almost sounds like music. Like, it almost sounds like the original sometimes, and then some other times it's just like in outer space. It's even funnier to me because, you know, I know these harmonies pretty well. Like, I'd say I've probably could reproduce like 50% of this piece from memory, and so it's hilarious to hear the moves in this kind of weird, messed up way. Although this is just incomprehensible now. It doesn't make any more sense. Yeah, there's actually a huge logic to this piece. It makes sense on a structural level. Because you have long-term harmonies that resolve over like multiple bars or even like the entire piece. So like when you mess up the where the notes go, it just sounds random. You know, it stops having that logic. Yeah, it doesn't really make any sense like this. Although we're getting near the end, so I'm curious to see how the ending goes. And you'll hear it when it jumps down. Very soon. Oh, actually, I skipped it. I missed it. Yeah, this is the ending. Funny. Okay, that is not the most exciting one, but it's interesting. Let's see what else I have. I have Für Elise by Beethoven. Let's try that. And let's hear it. The original. Oh, this might be loud, so maybe I should. Where is it? Where's the original? I want the original. Here. Oops. Okay. Everyone knows this, right? It's like every kid wants to play this piece. Ugh. It's like one of my least favorite Beethovens. Like it's just kind of a hack, but you know. Also, that part, everyone just plays it as like it's the Jaws theme. You know, it's just repeated notes, but that's not how it's supposed to be done. It switches between the hands there. So like, yeah, personal pet peeve. Let's hear it if played by Wednesday Addams. Actually, it's pretty intelligible. Okay, this part is just the repeated notes make it like the repeated notes are just like really hard to turn into a 12-tone thing because you have 12 tones to go through, and if you imagine repeating the same two notes for like the whole time, you need to map those notes somewhere. And so that's how you get that kind of complete mess there. Like, what is that even? Okay. Wow. That's okay. Last one for tonight. And then I promise I will stop hurting music. Let's see. I have, oh yeah, one of my favorite pieces. So this is Chopin's, it's commonly called Tristes, which is sorrow. And it's one of Chopin's etudes. And it's a beautiful piece. I played it for my ATCL. Not as well as Lang Lang or any other great pianist, but I did play it, and I don't remember how to play it anymore. Probably I would need the music at the very least. But we will try turning it into something ugly, because that's how this goes. You know, it's hard to make something beautiful. It's easy to make something ugly. So here's the output. Here's the original. You know what? Let's clear some stuff. Oh, never mind. Apparently the original is silent. So, yeah, something's wrong with that MIDI file. It won't play. So I guess Chopin is spared the antics of today, but the other composers are not so lucky. Hopefully they are not rolling in their grave too much, but that's it for today. thank you for dropping by, and I'll be back next week for more 12-tone shenanigans.